Most ancient civilizations are remembered through what they left behind, but some of the most unsettling mysteries come from what they did not leave behind. Entire populations vanished while their structures remained standing. Roads still lead to abandoned cities. Temples survive even after the beliefs that created them disappeared. In some places, traces of daily life suddenly stop as if history itself was interrupted. There are no complete records explaining every collapse, migration, or transformation. Only fragments remain, scattered across deserts, mountains, jungles, and forgotten coastlines. And the deeper archaeologists dig, the more the ancient world begins to feel less like a closed chapter and more like a puzzle with missing pieces. Because beneath the ruins and broken stone, there is still a larger story that has never been fully recovered. At first glance, this city should have been ordinary, yet everything about it feels unfinished, interrupted, and quietly unnatural. Just outside Bitola, the ruins of Heraclea Lyncestis lie along the ancient artery of Via Egnatia, a strategic route that once connected the Adriatic Sea to the eastern reaches of the Roman and Byzantine worlds. Founded in the 4th century BCE by Philip II of Macedon, the city should have evolved into a stable regional hub. Instead, its archaeological record tells a different story, one of repeated disruptions, unexplained abandonments, and a level of artistic and architectural precision that seems disproportionate to its status. Among all its mysteries, one stands out with unsettling clarity: the mosaics. They are not simply decorative. They are engineered surfaces that have survived more than 1,500 years with color stability and structural cohesion that still challenge modern assumptions about ancient materials. The site itself was never truly lost in the dramatic sense of forgotten cities swallowed by jungle or desert. Local awareness of the ruins persisted for centuries, but systematic archaeological investigation only began in the late 19th and early 20th centuries, when scholars working in the region of Ottoman Macedonia started documenting classical remains near Bitola. Excavations intensified during the 20th century under Yugoslav and later North Macedonian authorities, revealing layers that span Hellenistic, Roman, and Byzantine occupation. What emerged was not a single coherent city, but a sequence of urban phases repeatedly damaged, partially rebuilt, and then, at least in some periods, abruptly abandoned. Unlike sites such as Pompeii, where a single catastrophic event explains the archaeological snapshot, Heraclea presents multiple discontinuities without a single definitive cause. The first layer of mystery lies in those interruptions. Stratigraphic evidence suggests that certain occupation phases ended suddenly. Domestic objects remain in situ. Construction projects appear halted mid-process. In typical urban decline, especially in the late Roman world, we expect gradual contraction, public buildings repurposed, infrastructure deteriorating slowly, population thinning over generations. Here, however, there are hints of more abrupt behavioral shifts. Some researchers have linked these breaks to known historical pressures: Gothic incursions in the 3rd and 4th centuries CE, regional instability, or seismic activity in the Balkans. Yet none of these explanations fully account for the pattern. Earthquakes, for instance, leave distinctive collapse signatures, while invasions tend to produce burn layers, weapon remains, or mass destruction horizons. At Heraclea, the evidence is more ambiguous, suggesting disruption without a single, clearly identifiable trigger. But it is in the mosaics that the site becomes truly difficult to explain. The Byzantine basilicas of Heraclea contain floor mosaics that rank among the finest in the region, often compared to those of major centres such as Ravenna. At first glance, they follow familiar iconographic conventions, geometric patterns, vegetal motifs, and symbolic animals such as peacocks, which in early Christian art represent immortality. But a closer inspection reveals something more technical. The tesserae, the small pieces of stone, ceramic, or glass used to compose the images, are cut with remarkable uniformity, often measuring only a few millimeters across. Their placement is not merely aesthetic, it is structurally optimized. Angles, curvature, and spacing are adjusted to control how light interacts with the surface, producing a subtle but deliberate visual depth. What makes this particularly unusual is the durability of the color. After more than 1.5 millennia, many sections retain vivid contrasts, deep reds, saturated greens, and stable yellows, despite exposure to moisture, soil chemistry, and temperature fluctuations. Modern studies of ancient pigments show that many organic dyes degrade rapidly, while mineral pigments can remain stable but are often limited in chromatic range. Yet the palette at Heraclea suggests a more nuanced material selection. Some tesserae appear to incorporate iron-based oxides for reds and yellows, copper compounds for greens, and possibly imported stone types not native to the immediate region. This implies access to a broader material network than the city's size would suggest. When compared to Pompeii, where frescoes have also preserved strong coloration due to rapid burial under volcanic ash, the difference becomes significant. Pompeii's preservation is partly accidental, a product of an oxygen-poor environment that halted degradation. Heraclea's mosaics, by contrast, survived in open or semi-buried conditions. Their longevity is therefore not just a matter of circumstance, but of construction. The binding layers beneath the tesserae, composed of lime mortar, crushed ceramics, and carefully graded aggregates, form a multi-layered system that distributes stress and resists cracking. This technique is documented in Roman treatises such as those attributed to Vitruvius, yet the execution here appears unusually consistent and precise. The question is not whether ancient craftsmen were skilled; they undoubtedly were, but whether the level of optimization seen here exceeds what was functionally necessary. Floors needed to be durable and decorative, but not necessarily engineered to maintain chromatic integrity for over 15 centuries. That raises a deeper possibility, that certain knowledge of material behavior, how pigments interact with binders, how microstructures resist environmental stress was more advanced, or at least more systematically applied, than surviving texts indicate. If so, then part of that knowledge may have been lost, fragmented across regions, or simply never recorded in detail. Beyond the mosaics, the architectural layout of Heraclea adds another layer to the puzzle. The basilicas exhibit strong axial symmetry, with nave and aisles proportioned according to ratios that align with broader Roman and Byzantine design principles. Columns are spaced with regular intervals, and the transition between public and liturgical spaces is carefully managed. This is not unusual in major urban centers such as Rome or Constantinople, but Heraclea was, by comparison, a provincial city. The presence of such refined planning raises questions about the transmission of architectural knowledge. Were standardized blueprints circulating across the empire? Were itinerant architects responsible for disseminating design principles? Or does this reflect a local tradition that has left few written traces? The theatre of Heraclea, too, reflects a level of technical competence that borders on the intuitive understanding of physics. Like the famous theatre at Epidaurus Theatre, it is capable of projecting sound from the stage to the upper seating tiers with minimal loss of clarity. Modern acoustic analysis of Greek theatres has shown that factors such as seat geometry, limestone absorption properties, and the curvature of the seating area all contribute to this effect. Yet ancient builders lacked formal acoustic theory in the modern sense. Their success suggests either a long process of empirical refinement or a practical knowledge system that has not been fully reconstructed. And then there is the question of disappearance, not of the ruins themselves, but of their historical voice. For a city positioned on Via Egnatia, one of the most important roads of the Roman world, Heraclea is surprisingly underrepresented in written sources. Major trade routes typically generate administrative records, inscriptions, and references in historical texts. While some inscriptions have been found at the site, they do not fully explain its role within the regional economy. This silence is not total, but it is disproportionate. It suggests that either the city's importance has been underestimated, or that parts of its historical record have been lost, destroyed, or never extensively produced. What do you think really happened here? And are these mosaics just art, or evidence of something we've already forgotten? Let me know your thoughts in the comments below. Low, almost invisible against endless rice fields in West Java, the Batujaya temple complex does not look like a monumental achievement. There are no towering stone pyramids, no mountain-carved sanctuaries, no massive megaliths defying gravity. Instead, what remains are low brick mounds, subtle, fragmented, and easily overlooked. Yet beneath this apparent simplicity lies one of the most technically puzzling archaeological sites in Southeast Asia. The greatest mystery is not what was built, but how it survived. Constructed between the 5th and 7th centuries CE, likely during the era of the Tarumanagara, Batujaya exists in an environment where architecture should fail. Flood-prone plains, unstable alluvial soil, and constant humidity. And yet, after more than 1,500 years, its structures persist. Not intact, but undeniably present, defying the expected lifespan of their materials. Compared to monumental stone complexes like Borobudur, built centuries later on stable volcanic hills, Batujaya represents a paradox, a fragile technology, enduring where stronger systems might not. The rediscovery of Batujaya was not a dramatic archaeological breakthrough, but a gradual realization. Throughout the early 20th century, local farmers repeatedly encountered bricks, pottery fragments, and structural remnants beneath their fields. These findings were initially dismissed as isolated debris. It was not until systematic surveys in the 1980s that archaeologists began mapping the area and identified over 30 distinct mounds, known locally as Unia. Excavations revealed foundations, stair structures, and remnants of stupas, including the now famous Segaran site. Radiocarbon dating of organic inclusions within the bricks suggested a construction period ranging from approximately the 5th to 7th centuries CE. This predates the peak of classical Javanese temple construction, raising an important question: was Batujaya an early experimental phase of Buddhist architecture in the region, or something entirely different? Unlike centralized complexes, its structures are distributed across several square kilometers, with no clear urban core, defensive walls, or royal compounds, suggesting a function that does not align with typical ancient city planning. At first glance, Batujaya seems to represent an early form of Buddhist architecture, simple stupas constructed with limited technological means. However, several inconsistencies complicate this interpretation. Compared to Borobudur, which contains over 2,000 relief panels and more than 500 Buddha statues, Batujaya presents minimal iconography. The lack of detailed carvings or symbolic narratives suggests either a different ritual function or a stage of development not yet fully defined. Spatially, the structures are dispersed rather than centralized. Some are separated by hundreds of meters, forming what appears to be a decentralized ritual landscape rather than a unified ceremonial complex. Stratigraphic evidence further reveals that multiple structures were built atop earlier ones, indicating repeated reconstruction over extended periods. This layered construction suggests continuity, an evolving system, rather than a single architectural event. Yet no written records or inscriptions have been found to explain its purpose, leaving only physical patterns without explanatory context. The most critical and least understood aspect of Batujaya lies in its material composition. Unlike the volcanic stone used in Borobudur or the sandstone of Angkor Wat, Batujaya is constructed almost entirely from fired clay bricks. Under normal environmental conditions, such materials are inherently vulnerable. In tropical climates characterized by high humidity, seasonal flooding, and microbial activity, clay bricks typically degrade within a few hundred years. However, Batujaya's bricks have endured for more than 15 centuries. Scientific analyses reveal that these bricks are not compositionally ordinary. Many samples contain significant quantities of rice husk, an organic additive that burns out during firing, leaving behind a network of microscopic voids. These voids may function as internal channels, allowing moisture to diffuse rather than accumulate, thereby reducing structural stress. In addition, elevated silica content has been detected in several samples. Silica-rich compositions can enhance resistance to chemical weathering and increase mechanical stability under fluctuating moisture conditions. Together, these properties suggest a material system optimized not for maximum hardness, but for environmental compatibility. From a comparative perspective, this is significant. Roman concrete, known for its durability, relies on volcanic ash to create a pozzolanic reaction that strengthens over time. Batujaya, by contrast, appears to achieve long-term stability through porosity control and organic integration, an entirely different approach to material engineering. While Roman techniques are well documented, no equivalent records exist for Batujaya. This raises the possibility that early builders in Java developed an empirical understanding of material science that has since been lost. Whether this knowledge was intentional or the result of iterative experimentation remains unclear, but the outcome suggests a level of technical adaptation not typically associated with early brick architecture. Equally perplexing is the geotechnical context of Batujaya. The site is located on an ancient floodplain composed of soft alluvial sediments, a substrate that modern engineering would classify as highly unstable. Construction on such terrain typically requires deep foundations, soil stabilization, or drainage systems, none of which have been clearly identified at Batujaya. There are no stone platforms, no deep piling systems, and no visible hydraulic infrastructure capable of long-term water management. Yet the structures have not undergone catastrophic collapse. One proposed explanation is load distribution. The use of layered brick foundations may have spread structural weight over a larger surface area, reducing localized adduct on the soil. Another hypothesis suggests the existence of organic base layers, possibly bamboo or timber grids that have decomposed over time, leaving no direct archaeological trace. Both theories remain speculative due to the absence of preserved evidence. What is clear is that the builders operated within a highly dynamic environment, subject to periodic flooding and soil movement, and yet achieved a degree of structural persistence that challenges modern assumptions about early construction capabilities. When compared to other ancient sites, Batujaya stands out not for its scale, but for its contradiction. Monumental complexes like Borobudur and Angkor Wat demonstrate advanced geometry, symbolic complexity, and large-scale coordination. Batujaya, in contrast, employs minimalistic forms and modest materials, yet its survival in a hostile environment suggests a different kind of sophistication, one rooted not in grandeur, but in adaptation. In engineering terms, Batujaya may represent a system optimized for environmental integration rather than resistance. If so, it challenges the conventional assumption that ancient technological advancement is always expressed through monumentality. If you were tasked with building a structure to survive for over 1,000 years in a floodplain, using only natural materials, what principles would you rely on, and could you recreate what Batujaya achieved? Built at the foot of an ancient volcanic hill, rising as a fully planned capital in the late 15th century, and beneath it, an invisible system of water engineering so precise that it still challenges modern understanding. At the base of Pavagadh Hill in western India lies the Champaner-Pavagadh Archaeological Park, a site recognized by UNESCO as one of the most complete pre-Mughal Islamic cities ever preserved. Yet completeness is not what makes Champaner mysterious, because what makes it unsettling is this. It was engineered like a system and then abandoned like a prototype that was never meant to last. Unlike many ancient sites buried deep beneath the earth, Champaner was never truly lost, as local communities had always known of its ruins scattered across forests and farmland. But systematic archaeological attention only intensified during the 20th century, when surveys began revealing something unexpected. Not a random accumulation of ruins, but an intact urban system, where excavations and architectural mapping showed a fortified hilltop complex rising over 800 meters. A lower city with planned streets and districts, religious, military, and residential structures aligned along geometric axes, and most critically, a vast hydraulic infrastructure integrated into every level of the city, while carbon dating, stylistic analysis, and inscriptions link the majority of construction to the reign of Mahmud Begada, who ruled from 1458 to 1511 and sought to establish Champaner as his new capital. Yet what archaeologists uncovered went beyond political ambition, revealing a level of engineering precision that seemed disproportionate to the historical record itself. The most profound mystery of Champaner lies underground, where at first glance the site appears to contain typical South Asian stepwells, deep stone-lined shafts with descending staircases used to access groundwater. But deeper analysis reveals something far more complex. Because Champaner's water system was not a collection of isolated wells, but a coordinated hydraulic network spanning the entire city, engineered across a vertical landscape from the summit of Pavagadh Hill down to the plains below, where instead of relying on a single source, engineers designed a cascading system in which rainwater was captured at higher elevations, channeled through stone-lined conduits, stored in intermediate reservoirs, and then redistributed to lower zones, creating a gravitational system that required no mechanical pumps, yet maintained consistent water availability across different elevations, a challenge even modern infrastructure must carefully model. And when compared to Roman aqueducts that operated with gradients as low as 0.15% over long distances, Champaner required similar precision but in a far more complex vertical terrain, raising a critical question, not of capability, but of calculation, how such gradients were measured and maintained without surviving documentation. One of the most striking elements of this system is the so-called helical valve, a spiral stepwell descending into the earth through a circular shaft approximately 5 to 7 meters in diameter, where a continuous spiral staircase wraps downward along the interior wall, with evenly spaced steps that maintain structural balance, a design that reduces erosion by distributing load, stabilizes surrounding soil, and allows access to water across fluctuating levels without steep vertical drops, reflecting a deep understanding of geometry and load distribution. Because spiral stone architecture is notoriously difficult, and even in later medieval European fortifications required advanced planning, yet here it appears centuries earlier, executed with remarkable precision, without surviving manuals or engineering texts, leaving only the structure itself as evidence of knowledge that was clearly systematic but is no longer documented. Beyond structure, the system also suggests an understanding of water quality, as archaeological studies indicate that certain reservoirs were designed with sedimentation zones, where heavier particles could settle before water moved onward, implying awareness of contamination, intentional purification processes, and a multi-stage system resembling modern filtration principles, especially when contrasted with many medieval cities in Europe that struggled with polluted water sources and recurring disease outbreaks. While Champaner appears to have implemented environmental engineering strategies rarely recorded for its time, further reinforced by its adaptation to Gujarat's semi-arid climate, where seasonal monsoons create extreme fluctuations in water availability, yet the city's system buffered these variations through deep wells reaching stable groundwater, surface reservoirs capturing monsoon rainfall, and redundant storage networks distributed across elevations, aligning closely with modern hydrological principles that emphasize redundancy and distributed storage, suggesting that Champaner was not only engineered for survival but optimized for long-term environmental stability centuries before such concepts were formally defined. The city's structures reinforce the impression of advanced planning, most notably in the Jami Masjid Champaner, which stands as one of the finest examples of Indo-Islamic architecture, featuring more than 170 carved pillars, domes aligned with near-perfect symmetry, and intricate geometric motifs repeated with minimal deviation, where detailed measurements indicate that many carvings exhibit tolerances within just a few millimeters, a level of consistency that raises difficult questions because while manual carving can achieve artistic beauty, uniform precision at this scale suggests the use of standardized measurement systems, possible templating techniques, or lost methods for transferring geometric patterns efficiently, and when compared to contemporary structures in Central Asia or the Middle East, Champaner's craftsmanship proves equally sophisticated not only in aesthetic execution, but in technical accuracy. Above the city rises the fortified complex on Pavagadh Hill, where transporting stone blocks to elevations exceeding 800 meters would have required coordinated labor forces, temporary infrastructure such as ramps or scaffolding, and precise planning to align structures on uneven volcanic terrain. Yet physical evidence of such large-scale transport systems remains minimal, with no extensive ramp structures preserved and no clearly identifiable quarry-to-summit pathways, a problem that echoes similar unresolved questions at sites like Machu Picchu in Peru. Though Champaner's volcanic geology introduces additional complications, including irregular rock surfaces, steep gradients, and limited stable footing, making the successful construction of aligned, durable structures at such heights even more remarkable. In 1535, the Mughal Emperor Humayun captured Champaner, and within decades the city declined. Yet what remains puzzling is not the fall itself, but the nature of its abandonment. Because there is no widespread destruction layer, no clear evidence of catastrophic collapse, and no large-scale burning across the urban landscape, suggesting that the city was not violently erased but rather gradually left behind, as if a functioning system had simply been switched off, leaving its water infrastructure intact beneath the ground, its buildings standing above it, and its engineering still present but no longer actively maintained. What do you think, was Champaner an isolated achievement, or evidence of a broader engineering tradition we have yet to fully uncover? Share your thoughts in the comments below. Just off the northeastern coast of Crete lies Mochlos, a rocky island barely large enough to sustain a small village, with no rivers, no farmland, and no strategic fortifications. And yet during the height of the Minoan civilization, roughly between 3000 and 1200 BCE, this seemingly insignificant landmass became something far more complex, a hub of production, exchange, and possibly controlled knowledge, where archaeological evidence reveals advanced metallurgy, long-distance trade, and architectural precision emerging from a place that, by every geographic and logistical metric, should have remained peripheral, creating a contradiction that defines the mystery itself. Because Mochlos does not behave like a settlement, it behaves like a system. The modern understanding of Mochlos began in the early 20th century, when American archaeologist Richard Seeger conducted excavations between 1904 and 1906, uncovering over 30 stone-built tombs filled with finely crafted goods, such as gold jewelry, carved seals, and imported stones. And later excavations led by Jeffrey Soules revealed dense architectural remains including workshops, storage areas, and what appears to be a harbour-facing production zone. And although population estimates based on housing density suggest only a few hundred inhabitants, the volume and sophistication of artefacts indicate an economic output far beyond local needs, establishing a fundamental mismatch between scale and capability that defines Mochlos. Among the most debated discoveries at Mochlos are its gold artifacts, many of which reveal under magnification the use of granulation, a technique in which microscopic spheres of gold are fused onto a surface to create intricate geometric and organic patterns, with some granules measuring less than 0.5 millimeter in diameter. And experimental archaeology has demonstrated that achieving consistent granulation at this scale requires temperature control within a narrow range of approximately 800 to 900 degrees Celsius, because temperatures too low prevent bonding while temperatures too high cause the particles to collapse into amorphous masses. Yet the granules at Mochlos are not only uniform in size, but also symmetrically arranged and fused without visible solder lines, flux residues, or binding agents, indicating a level of thermal precision and process control that appears disproportionate to the technological context of the Bronze Age, raising the question of how such artisans monitored and stabilized temperature without instruments, especially when similar levels of granulation are more commonly associated with the Etruscan civilization more than 1,000 years later. And although metallurgical studies suggest the possible use of charcoal furnaces with forced airflow generated by bellows systems capable of increasing combustion efficiency and heat stability, no definitive remains of such advanced installations have been identified at Mochlos itself, leaving the operational infrastructure behind this precision largely speculative, while trace element analysis further reveals deliberate alloying of gold with silver and copper in controlled ratios to manipulate hardness, melting point, and color tone, indicating not only empirical skill but predictive understanding of material behavior, suggesting that the artisans were not simply experimenting but operating within a refined technical framework. And when these factors are considered together, the evidence points toward a production system that was controlled, repeatable, and optimized, resembling a specialized metallurgical industry rather than a localized craft tradition, raising the possibility that Mochlos functioned as a restricted center of high-precision manufacturing embedded within broader trade and knowledge networks that have not yet been fully reconstructed. The architectural remains at Mochlos reveal walls constructed from cut stone blocks with tight-fitting joints and minimal use of mortar, where some surfaces appear smoothed and leveled beyond what is typically achievable with basic Bronze Age stone tools, suggesting controlled shaping and finishing processes. And this style resembles early forms of ashlar masonry that would later become more widespread in advanced architectural contexts, and comparisons are often drawn to sites such as Machu Picchu, where stone fitting reaches extreme precision, despite being separated by more than 2,000 years and vast geographic distance. Yet at Mochlos such techniques appear in a setting lacking the political scale, monumental architecture, or ceremonial complexity typically associated with high-investment construction, which raises the question of why such precision was applied in what should have been a relatively modest settlement, suggesting either the presence of specialized builders or the transfer of architectural knowledge into a context that does not align with traditional models of technological diffusion, reinforcing the idea that Mochlos operated under conditions that allowed advanced techniques to exist independently of large-scale urban or imperial frameworks. Material analysis shows that artifacts from Mochlos include obsidian traced to Milos, as well as lapis lazuli likely originating from northeastern Afghanistan, one of the few known ancient sources of this mineral, along with additional evidence suggesting contact with Egypt and the Levant through stylistic parallels and compositional signatures, placing Mochlos within a vast maritime network extending across thousands of kilometers. Yet despite this extensive connectivity, the island shows no evidence of large-scale storage facilities, centralized warehouses, or shipbuilding infrastructure that would normally accompany a major trading hub, suggesting instead that Mochlos functioned as a high-efficiency processing node where materials were received, transformed, and redistributed rather than accumulated, operating more like a relay point within a distributed system than a conventional port city. And this interpretation aligns with the observed mismatch between artifact complexity and settlement scale, reinforcing the idea that Mochlos played a specialized role within a larger economic and technological network that extended far beyond its physical boundaries. Certain architectural zones at Mochlos differ from residential and industrial areas, consisting of small enclosed rooms with repetitive layouts and containing objects that appear ceremonial rather than functional, while tombs associated with the site contain items of disproportionately high value relative to the scale of the community, including finely crafted metal objects and imported materials, suggesting that Mochlos may have functioned as a controlled environment in which specialized knowledge, particularly metallurgical techniques, was restricted to a select group, implying a social structure in which technical expertise was not widely distributed but concentrated and possibly protected. And this interpretation provides a potential explanation for the high level of craftsmanship observed at the site without requiring the entire population to possess such skills, indicating that Mochlos may represent not a typical settlement, but a localized center of specialized production operating under conditions of controlled access and knowledge limitation. Around 1500 BCE, Mochlos experienced a period of destruction likely connected to the eruption of Thera, an event that geological evidence suggests caused widespread ash fallout, atmospheric disruption, and possible tsunami activity across the Aegean region. And although some level of reoccupation occurred after this event, the intensity and complexity of activity at Mochlos never returned to its earlier peak, and more significantly, certain techniques, particularly in fine metalwork, appear to decline or shift in character, indicating not only physical disruption, but also a breakdown in the transmission of technical knowledge, suggesting that whatever system had supported the high level of craftsmanship at Mochlos was either dismantled or no longer sustainable after the environmental and social shocks associated with the eruption. What do you think Mochlos really was, just a trading outpost, or something closer to an ancient technological hub? Share your thoughts in the comments below. Southwestern Turkey, near the modern province of Burdur, lies a Neolithic settlement dated between approximately 7000 to 5600 BCE. By conventional archaeological models, this period represents early farming communities, small, experimental, and technologically limited. Yet Hacilar does not behave like an early experiment. It behaves like a refined system, and the most unsettling detail is not its age but its precision. Ceramics with controlled firing, architecture with repeatable standards, and symbolic art with consistent form, none of which appear accidental, instead suggesting knowledge that seems too organized, too optimized, and too early. When compared to contemporary sites across Mesopotamia and Anatolia, Hacilar appears to compress centuries of development into a much earlier phase, raising a question that remains unresolved. Was this a local anomaly, or a fragment of a larger, lost knowledge system? Hacilar was systematically excavated in the late 1950s by British archaeologist James Mellart, the same figure associated with Çatalhöyük. And what emerged from the excavation was not a single settlement, but a sequence of multiple stratified layers indicating long-term occupation. Each layer revealed variations in construction techniques, pottery styles, and social organization, pointing to gradual development over time. Yet what surprised researchers was not the presence of development, but its starting point. Because even the earliest layers already displayed structured housing clusters, advanced ceramic production, and repeated symbolic motifs. While radiocarbon dating confirmed the age and firmly placed Hacilar within early Neolithic timelines, technologically it appeared closer to later Chalcolithic cultures, creating a discrepancy that has never been fully reconciled. Among all findings, Hacilar's ceramics remain the most difficult to explain within a linear technological model, because these vessels are not crude containers but engineered objects, beginning with their geometric precision, where patterns are arranged with near-perfect bilateral symmetry, lines maintain consistent thickness, curvature follows predictable arcs, and spacing remains uniform across the surface. And achieving this without rotational tools or measurement instruments implies either extraordinary manual control or a standardized production system that has left no clear archaeological trace. Beyond geometry, the surface finish reveals another layer of complexity, as many vessels exhibit a highly polished, almost burnished exterior produced through controlled abrasion techniques, with microscopic analysis suggesting repeated smoothing cycles using fine-grained materials, a level of effort that exceeds basic functional needs and points toward deliberate refinement, while the most critical factor lies in firing control, where the red and black color contrasts are not decorative accidents but the result of precise oxygen regulation during firing, with oxidizing conditions producing red hematite tones and reducing conditions creating darker carbon-rich surfaces. And experimental archaeology demonstrates that achieving such effects requires stable kiln temperatures, likely exceeding several hundred degrees Celsius, carefully managed airflow and fuel distribution, and precise timing sequences to regulate oxygen exposure. Yet no fully developed kiln infrastructure has been definitively identified at Hacilar, creating a paradox in which the outputs suggest advanced kilns, while the physical evidence suggests simpler systems. When compared to early Neolithic ceramics from the Levant, which often display uneven firing and irregular decoration, Hacilar pottery aligns more closely with later Bronze Age standards, representing not an incremental improvement, but a categorical leap. And further analysis of ceramic shards reveals relatively consistent wall thickness within narrow tolerances, indicating a level of process control rather than random craftsmanship, and suggesting that production may have been guided by shared technical knowledge or early specialization, ultimately shifting the question from how these ceramics were made to why such precision was pursued at all. Because from a purely survival-based perspective, simple containers would have been sufficient. Yet Hacilar ceramics instead point toward aesthetic standardization, symbolic communication, or participation in a broader cultural or economic network, reinforcing the possibility that Hacilar was not an isolated settlement, but part of a larger information system, transmitting techniques, patterns, and meaning across space and time. The settlement's architecture appears simple at first glance, consisting of mud brick walls, plastered interiors, and flat surfaces, yet this simplicity conceals a deeper complexity, because mud brick is inherently vulnerable to erosion from moisture and temperature variation. And despite this, the wall outlines and floor plans at Hacilar remain clearly identifiable after millennia, implying the use of multi-layer plastering techniques that improved resistance, possible additives in the mud mixture that enhance cohesion, and maintenance cycles that extended structural lifespan. And when compared to similar mud brick settlements in early Mesopotamia that often degrade into indistinct mounds, Hacilar retains a level of spatial clarity that suggests either an environmental advantage or a form of material knowledge that has not yet been fully reconstructed. The anthropomorphic figurines, particularly the female forms, introduce another layer of complexity as they are not naturalistic representations, but stylized constructions that emphasize posture and proportion over realism. And the repetition of these forms suggests the presence of a codified visual language, where meaning was embedded in shape, gesture, and proportion rather than written symbols. And without textual records, these objects may have functioned as cultural identifiers, ritual instruments, or carriers of abstract concepts. While their consistency across different occupation layers indicates continuity of meaning, even as other aspects of the settlement evolved. Perhaps the most subtle and revealing mystery lies not in what is present, but in what is absent, because there are no clear palaces, no monumental temples, and no obvious elite residences. Yet despite this absence, the settlement demonstrates organized architectural layouts, standardized ceramic production, and consistent artistic motifs, a level of uniformity that in later civilizations is typically enforced through hierarchical systems, and at Hacilar that hierarchy remains invisible, suggesting either an egalitarian system governed by strong cultural rules or a form of authority expressed through non-material means such as ritual, oral tradition, or symbolic systems that leave little archaeological trace. If knowledge like this existed so early, how much of human history are we missing entirely? Tell me your thoughts in the comments below. A vast geometric landscape rises quietly along the banks of the Black Warrior River in Alabama, United States. At first glance, Moundville appears simple earth mounds arranged around an open plaza. No towering stone, no inscriptions, no obvious machinery. And yet, beneath that simplicity lies one of the most unsettling paradoxes in North American archaeology. A prehistoric society, dating roughly from 1000 to 1450 CE, constructed a highly ordered, 12, large-scale urban and ceremonial complex with a level of spatial precision, engineering control, and astronomical awareness that seems disproportionate to the tools it supposedly possessed. The most mysterious element is not what stands, but how it was conceived, measured, and executed, without leaving behind the technical footprint we would expect from such achievements. Although known locally for centuries, Moundville only began to reveal its complexity through systematic investigation in the early 20th century. Archaeologist Clarence Bloomfield Moore conducted surveys between 1905 and 1906, documenting the site's scale and recovering artifacts that hinted at a far more sophisticated culture than previously assumed. Later excavations throughout the 20th century expanded the dataset dramatically, revealing over 29 platform mounds, a central plaza spanning approximately 300 by 200 meters, and thousands of artifacts crafted from copper, shell, and stone. Radiocarbon dating placed peak occupation between approximately 1100 and 1450 CE, aligning the site with the broader Mississippian culture. Yet even at this early stage, something did not align with expectations. The layout was not random. It was deliberate, structured, and mathematically consistent, raising questions that excavation alone could not answer. Unlike stone-built civilizations such as Machu Picchu or Teotihuacan, Moundville relied almost entirely on earth, and yet its spatial organization rivals those sites in conceptual clarity. The mounds are arranged in a near-rectangular perimeter surrounding the central plaza, with consistent spacing and alignment that closely follows cardinal directions. Surveys have shown that deviations from true north are minimal, often within a few degrees, suggesting intentional orientation rather than coincidence. This level of precision becomes more striking when placed in context. The Mississippian culture lacked metal tools capable of fine measurement, had no written numerical system, and left no known architectural blueprints. Still, the result is a landscape that behaves like a planned environment rather than an organically grown settlement. The question emerges naturally. What system of measurement was used? Rope-based surveying, standardized pacing, celestial reference points? Each explanation solves part of the puzzle, but none fully accounts for the consistency observed across the entire site. Excavations into the mounds themselves revealed an even deeper layer of complexity. These were not simple piles of dirt. Stratigraphic analysis shows that the mounds were constructed using multiple distinct soil types, carefully layered in sequences that appear to serve structural purposes. Coarser materials were often placed at the base for drainage, while finer clays formed upper layers, increasing cohesion and stability. Modern geotechnical engineering uses similar principles, layering materials to manage load distribution, moisture retention, and erosion resistance. Yet at Moundville, these techniques appear without accompanying theory. There is no written record of soil mechanics, no evidence of formal experimentation, and no preserved tools designed specifically for compaction or grading. Despite this, many mounds have maintained their structural integrity for centuries, surviving seasonal flooding and environmental stress. The implication is difficult to ignore. Either this knowledge was empirically refined over generations to a high degree of accuracy, or it was part of a structured body of understanding that has since vanished without trace. Artifacts recovered from the site belong to what archaeologists classify as the Southeastern Ceremonial Complex. These include engraved copper plates, carved shell ornaments, and symbolic motifs such as the birdman, spirals, and hand-eye imagery. While often interpreted as religious or mythological, their repetitive geometric structure raises another possibility, that they encode patterns of knowledge. The precision of these designs, symmetry, proportion, repetition, mirrors the spatial logic of the site itself. In other ancient cultures, such as in Mesoamerica or ancient Egypt, symbolic systems often doubled as carriers of technical or cosmological information. If a similar function existed at Moundville, then the absence of written language does not necessarily imply the absence of structured knowledge. It may instead suggest a different medium of transmission, one that is far harder to decode. Among all the mysteries at Moundville, none is more compelling or more difficult to verify than the possibility of astronomical alignment. Several studies have proposed that the arrangement of mounds and the orientation of the plaza correspond to solar events, particularly the summer and winter solstices. Sightlines from specific mound summits appear to align with the position of the rising or setting sun at key points in the solar year. If accurate, this would place Moundville in conceptual alignment with sites such as Stonehenge, where massive stones mark celestial cycles, or even Chichen Itza, where architectural features create shadow effects during equinoxes. However, unlike these stone-built observatories, Moundville achieves similar potential functionality using only earth and spatial arrangement. The scientific challenge lies in distinguishing intentional alignment from coincidental geometry. Given the number of mounds and possible sightlines, statistical probability must be carefully considered. Yet some alignments are difficult to dismiss. For example, the central axis of the plaza has been noted to approximate east-west orientation, while certain mound placements correspond to solar azimuth angles observed at this latitude. At approximately 33 degrees north latitude, the sun's position at solstices shifts significantly along the horizon. Calculating these positions without instruments requires long-term observation and precise memory. To encode that knowledge into permanent architecture suggests not only awareness of celestial cycles, but also a cultural need to preserve and transmit that information. This leads to a deeper question. Was Moundville functioning as a ceremonial center synchronized with a solar calendar? Or was it something more, a place where time itself was structured, observed, and perhaps even controlled through spatial design? Across all dimensions, geometry, engineering, symbolism, and astronomy, Moundville presents a consistent pattern. The results are visible, measurable, and in many cases comparable to other ancient civilizations. Yet the processes behind those results remain almost entirely absent from the archaeological record. There are no surviving instruments, no clear construction sequences beyond what soil layers imply, no instructional artifacts that describe how measurements were taken or alignments determined. Even the labor organization required to move and shape thousands of cubic meters of earth remains only partially understood. This absence creates a paradox. In modern terms, complex output typically correlates with complex tools and documentation. At Moundville, the output exists without the expected infrastructure. Either the tools were perishable and lost, or the methods themselves relied on principles that leave little physical trace: human coordination, oral transmission, and repeated observation over generations. What do you think? If a civilization can embed astronomical knowledge, engineering principles, and spatial precision into Earth itself, without written records or advanced tools, are we underestimating how knowledge once existed and evolved? Tell your thoughts in the comments below. On the northern coast of Milos, an island shaped by volcanic fire in the heart of the Aegean Sea, lies a settlement that defies expectations. No towering pyramids, no colossal temples. And yet, Phylakopi presents a more unsettling mystery than most monumental civilizations. How did a relatively small island community achieve a level of engineering continuity, artistic sophistication, and maritime integration that rivals far larger Bronze Age powers? Between approximately 3000 and 1100 BCE, Phylakopi evolved through multiple phases of occupation, each layer building upon the last. Archaeological estimates suggest sustained habitation for over a millennium, an unusually long continuity for a settlement of its scale. In comparison, even major centers like Troy experienced repeated destruction cycles that reset their urban development, while Phylakopi appears to have preserved and adapted its knowledge across generations. The question is not whether it was advanced, but how such advancement was maintained, and why it seems disproportionate to its size and resources. The systematic excavation of Phylakopi began in the late 19th century under the direction of the British School at Athens, where early campaigns revealed something unexpected. Instead of a single city, archaeologists uncovered a sequence of superimposed urban phases categorized as Phylakopi I through IV. Stratigraphic analysis shows continuous rebuilding over earlier foundations, structural reuse rather than full demolition, and gradual architectural refinement over centuries. while radiocarbon dating and ceramic typology confirm a timeline stretching from the early Cycladic period to the late Bronze Age. Unlike sites that exhibit abrupt cultural breaks, Phylakopi demonstrates incremental technological evolution, suggesting a stable transmission of knowledge across generations. This continuity raises a critical question. What mechanisms allowed technical knowledge to persist without clear written records? In its later phases, Phylakopi was enclosed by fortifications constructed in the Cyclopean-style massive, irregular stone blocks fitted together without mortar, a technique famously associated with Mycenae. Yet here lies the anomaly, because Mycenae was a major political and military hub with access to vast labour and resources, while Phylakopi was not. Measured blocks at comparable sites often weigh between 2 and 10 metric tons, and although those at Phylakopi are generally smaller, their placement still requires coordinated lifting, alignment, and stabilization techniques that imply organized labor and mechanical understanding. The lack of definitive evidence for advanced lifting devices, the absence of quarry infrastructure matching the scale of construction, and the structural precision exceeding what is expected from simple stone tools all contribute to the unresolved nature of these fortifications. When compared to other Bronze Age defensive systems, Phylakopi's walls appear functionally excessive, suggesting either a perceived threat not fully understood or a cultural and technological influence imported from more powerful civilizations. Despite limited agricultural potential, Phylakopi became a significant node in Aegean trade networks, with its strategic importance tied to obsidian, a volcanic glass sourced abundantly on Milos. Chemical sourcing studies have confirmed that obsidian from Milos reached mainland Greece and Crete as early as the Neolithic period, and at Phylakopi archaeologists have identified imported ceramics, Mycenaean cultural influences, and evidence of long-distance exchange across the Cyclades. This implies a sustained maritime network operating across hundreds of kilometers of open sea. Yet there is no evidence of navigational instruments such as compasses, no written maritime charts, and no standardized port infrastructure. Experimental archaeology suggests that Bronze Age sailors relied on celestial navigation, wave patterns, and seasonal wind systems. But the consistency required to maintain such trade over centuries remains difficult to fully explain. Compared to later Mediterranean systems, Phylakopi's network appears prematurely sophisticated, hinting at a level of maritime knowledge that was never formally recorded. Among the most compelling discoveries at Phylakopi is the famous flying fish fresco, a vibrant wall painting that has survived for over 3,000 years, and while it visually resembles the frescoes of Akrotiri, closer analysis reveals deeper unanswered questions. Fresco painting involves applying pigments onto wet plaster so that the color chemically bonds with the wall as it dries, a technique that is well understood, yet the longevity and vibrancy of the pigments at Phylakopi are unusual even by known standards. Scientific observations indicate that the pigments were likely derived from mineral sources, such as iron oxides and copper compounds, that they have remained stable despite exposure to humidity and salt-laden air, and that they show minimal degradation compared to similar aged works. In controlled studies, many natural pigments degrade significantly within centuries under coastal conditions, yet at Phylakopi the colours remain strikingly intact, suggesting either advanced selection and processing of mineral pigments, specific plaster compositions that enhance chemical bonding, or environmental sealing conditions that are not yet fully understood. However, no definitive experimental reconstruction has successfully replicated the exact durability observed. When compared to contemporaneous art traditions, Egyptian wall paintings often relied on dry pigment application and show different aging patterns. While Minoan frescoes at Akrotiri were preserved largely due to volcanic ash burial, a protective condition that Phylakopi lacks, making its preservation more difficult to explain. This leads to a deeper and more provocative question. Did Bronze Age artisans possess a more refined understanding of material chemistry than modern archaeology currently assumes? Phylakopi does not follow the rigid grid systems seen in cities like Mohenjo-Daro, yet its layout is far from random, as spatial analysis reveals consistent access routes between key areas, functional zoning of residential and communal spaces, and efficient use of terrain and elevation. This suggests a form of adaptive planning in which the city evolves in response to environmental constraints rather than imposing strict geometric order, a concept that modern urban theory would later describe as organic planning. The presence of such planning principles in a Bronze Age settlement challenges assumptions about the development of urban design and indicates that sophisticated spatial reasoning existed long before formalized architectural theory. Perhaps the most profound mystery lies in the continuity of Phylakopi itself, because over more than 1,000 years the settlement was repeatedly rebuilt on existing foundations, its structural techniques improved, and external cultural influences integrated without disrupting its overall coherence. Despite this, no extensive written records have been found, and unlike civilizations such as those of Mesopotamia that relied heavily on written documentation to preserve technical knowledge, Phylakopi appears to have transmitted its expertise through apprenticeship systems, oral tradition, and repeated construction practices. Such methods are inherently fragile and typically degrade over time, yet in this case they did not, suggesting an unusually stable system of knowledge transmission that has left behind physical results but no clear explanation of how that knowledge was preserved. What do you think, was Phylakopi truly advanced beyond its time? Or are we underestimating how capable ancient societies really were? Share your thoughts in the comments below. Civilizations do not normally build more than 100 temples without a clear, unified design. Yet in the rugged landscape of Aihol, along the banks of the Malapraba River, a contradiction emerges that challenges both logic and historical expectation. Dating primarily between the 6th and 8th centuries CE under the Chalukya dynasty, this site contains over 120 structures, each one slightly different, each one seemingly testing a new idea. The mystery is not just what Aihol is, but what it was trying to become. Unlike other ancient centers where architectural evolution follows a gradual and traceable progression, Aihol compresses experimentation into a single geographic space. Styles that should be separated by centuries appear side by side. Forms that belong to different cultural traditions coexist without clear hierarchy. The result feels less like a finished city and more like a controlled environment, an ancient laboratory of stone. Aihol was not discovered in the traditional sense. Local communities had always known of its existence, but systematic study began during the 19th century under the Archaeological Survey of India. Early documentation revealed something unusual. These temples were not built in a linear sequence, but in overlapping phases, often modifying or reinterpreting earlier designs. One of the most important clues comes from the Maguti Jain temple inscription, dated to approximately 634 CE. This inscription anchors Aihol historically, linking it to the Chalukya king Pulakeshin II. However, archaeological analysis shows that many structures predate and postdate this inscription, suggesting continuous experimentation over multiple generations. Excavations have uncovered not only foundations and structural modifications, but also evidence of architectural adjustments mid-construction, walls shifted, columns repositioned, and layouts altered. Such changes imply that builders were not simply executing plans, they were revising them in real time. The most unsettling mystery at Aihole lies not in its diversity, but in its precision. Many of the temples were constructed using dry stone techniques, blocks fitted together without mortar. Yet the joints are so exact that even modern measuring tools struggle to detect gaps beyond fractions of a millimeter. From an engineering perspective, this level of accuracy exceeds functional necessity. A stable structure does not require such perfection. In fact, in many ancient systems, slight irregularities help distribute stress more evenly. Yet at Aihole, stones are cut and aligned with a degree of geometric control that suggests an advanced understanding of load transfer and material behavior. Consider the placement of stone beams and ceiling slabs. Some of these elements weigh several tons, yet they are supported by relatively narrow columns. Modern structural analysis indicates that the load distribution in such systems depends on precise alignment of contact surfaces. A deviation of even a few degrees could significantly increase stress concentrations. The builders of Aihole appear to have anticipated this, achieving tolerances comparable to finely machined components. When compared to Roman engineering such as the arches of the Colosseum, the contrast becomes clear. Roman builders relied on arches and concrete to redistribute forces efficiently across curved surfaces. At Aihole, however, the approach is fundamentally different. Instead of dispersing stress through curvature, the structures concentrate load through carefully controlled Nakort Teepsukdar, stone contact points, almost as if the builders were experimenting with micro-load balancing systems. There is also evidence of interlocking mechanisms in certain structures, where stones are shaped to fit into each other in ways that prevent lateral movement. This technique, while known in other ancient cultures, appears here in a more experimental and inconsistent form, as if multiple solutions were being tested simultaneously. The question that emerges is unavoidable. Why invest such effort into precision that provides no immediate practical advantage? One possibility is that Aihole served as a testing ground for structural optimization, an attempt to understand how stone behaves under different conditions. Another, more controversial hypothesis suggests that the builders possessed a theoretical framework, perhaps a form of early applied geometry or proto-engineering science, that has not survived in written form. Aihole is often described as the cradle of Indian temple architecture, but this label does not fully capture its complexity. The site contains early examples of multiple architectural traditions: the northern Nagara style, the southern Dravida style, and the hybrid Visara form. What is unusual is not their presence but their coexistence. In most historical contexts, these styles emerge in different regions and evolve over time. At Aihole, they appear together, sometimes within a single structure. The Durga temple, for instance, features an apsidal plan reminiscent of earlier Buddhist Chaitya halls, combined with elements that would later define Hindu temple architecture. Meanwhile, the Ladkhan temple resembles a secular assembly hall with a flat roof supported by massive stone beams, lacking the vertical emphasis typical of later temples. Such diversity suggests that Aihole was not bound by a single religious or cultural framework. Instead, it appears to have been a place where ideas were tested, combined, and reinterpreted. Many ancient structures align with celestial events, but Aihole presents a more complex pattern. While some temples are oriented toward the east, others deviate slightly, creating variations in how sunlight enters the interior spaces. These deviations are not random. Observations suggest that different temples produce distinct light patterns at different times of the year. In certain cases, sunlight illuminates specific parts of the structure only during particular seasons, hinting at a deliberate manipulation of solar angles. Compared to monuments like Stonehenge, which exhibit precise alignment with solstices, Eyehole's approach appears less about exact calibration and more about exploring a range of possibilities. This raises the possibility that the site functioned as a form of experimental observatory, where builders studied the interaction between architecture and light. Perhaps the most intriguing aspect of Eyehole is its apparent incompleteness. Many structures show signs of partial construction, finely carved bases supporting unfinished upper sections, or detailed columns beneath rough, unpolished stone surfaces. In most archaeological contexts, such features indicate interruption, war, resource shortages, or abandonment. But at Eyehole, the pattern repeats across multiple sites, suggesting something else entirely. If these were prototypes rather than final products, their incomplete state may have been intentional. Each structure could represent a stage in an ongoing process, a snapshot of experimentation rather than a failed project. So what do you think Eyehole really was, an ancient architectural laboratory? Or something even more advanced that we still don't understand? Drop your thoughts in the comments below. In Gujarat, Vadnagar does not usually challenge how we understand ancient engineering, yet it quietly does exactly that. Because beneath its modern surface lies a settlement continuously occupied for more than 2,500 years, a rare archaeological phenomenon in South Asia. But continuity alone is not the mystery, as the deeper anomaly is structural, a pattern of urban planning, hydraulic control, architectural precision, and material durability that appears far too optimized for what should have been a modest regional town. And what ultimately emerges from Vadnagar is not a ruin, but a system operating across centuries. Vadnagar was never truly lost, as references to it persisted in historical records and the settlement remained inhabited. Yet systematic excavations carried out by the Archaeological Survey of India during the late 20th and early 21st centuries revealed a far more complex reality, uncovering deep stratified occupation layers extending back to at least the early historic period, potentially as early as the 6th century BCE, where each excavation phase exposed structured remains including fortifications, residential zones, drainage systems, and religious complexes stacked across time. And unlike many ancient cities such as Mohenjo-Daro, which show signs of abrupt decline or abandonment, Vadnagar demonstrates an unusual continuity, with later generations reusing earlier foundations with minimal disruption, suggesting not only continuous habitation but the preservation of spatial knowledge across centuries, a phenomenon rarely documented with such consistency in ancient urban environments. Ancient cities typically evolve in irregular and often chaotic ways, where roads shift, districts expand unpredictably, and structures are rebuilt without strict adherence to previous layouts. Yet Vadnagar diverges from this expected pattern in measurable ways, as archaeological surveys reveal the persistence of aligned primary streets across multiple occupational layers, the repeated reuse of foundational walls over centuries, and a consistent orientation of built structures often aligned with functional or cardinal axes. And when compared to highly organized cities such as Rome, which still underwent constant reconfiguration due to political, economic, and environmental pressures, Vadnagar instead appears to maintain a stable urban logic across time, implying either the existence of a transmitted planning tradition or a foundational design so efficient that it required little modification, both of which raise the same unresolved question of how such long-term consistency could persist without centralized imperial control or recorded planning doctrine. One of the most technically revealing aspects of Vadnagar lies beneath the surface, where excavations have uncovered an interconnected network of drainage channels, water storage systems, and stepwell-linked infrastructure. with key observations including channels constructed with carefully controlled gradients indicating deliberate slope calibration, segmentation between wastewater and cleaner water pathways, and evidence of seasonal water regulation likely adapted to monsoon cycles, all of which imply an applied understanding of fluid dynamics, sediment flow, and hydraulic control. And although such knowledge was not formally expressed in mathematical texts, its execution reflects practical engineering competence comparable in principle to Roman aqueduct systems, which maintained gradients as precise as 1 meter per kilometer over long distances. And while Vadnagar's systems operate on a smaller scale, they demonstrate a similar sensitivity to slope and flow consistency, making the anomaly not the existence of such knowledge, but its presence within a settlement that was neither a political capital nor a major population centre, yet still exhibits a level of hydraulic refinement disproportionate to its scale. Among all anomalies identified at Vadnagar, the most difficult to dismiss lies in the performance of its building materials, as excavated walls, foundations, and structural remains demonstrate remarkable preservation across centuries of climatic fluctuation, showing limited erosion despite repeated exposure to monsoon-driven moisture cycles, while brick dimensions remain highly consistent, indicating controlled production methods, and material analysis suggests that these bricks were fired at relatively high and stable temperatures with uniform heat distribution, a process that would have required precise control of fuel, kiln structure, and firing duration, while traces of mortar reveal binding agents with notable resistance to water infiltration. And although lime-based mortars were known in ancient India, the observed durability suggests either optimized compositions or environmental adaptations beyond typical construction practices, particularly when compared to many mud brick or even fired brick structures across South Asia, which often degrade within a few centuries without maintenance. And even at major sites such as Nalanda, extensive restoration has been necessary to preserve structural integrity, whereas Vadnagar presents sections where original materials remain intact without continuous intervention, leading to the critical possibility that its builders were not merely constructing functional spaces, but engineering materials with long-term performance in mind, implying an understanding of thermal behavior during firing, moisture interaction within structural systems, and resistance to environmental stress over extended periods, all of which point toward repeatable, controlled processes that resemble early forms of technological standardization rather than isolated construction efforts. The Buddhist monastery uncovered at Vadnagar adds another layer of complexity, as its layout reveals symmetrically arranged residential cells surrounding a central courtyard, with consistent room dimensions and clearly defined circulation pathways. And while standardization can improve efficiency and reduce construction variability, the degree of precision observed exceeds what would be strictly necessary for monastic life, particularly when compared to other ancient institutions such as Nalanda, where architectural variation reflects gradual expansion, whereas Vadnagar suggests a predefined modular design, raising the possibility that this was not simply religious architecture, but part of a broader planning philosophy applied across the settlement itself. Artifacts recovered from Vadnagar, including coins, ceramics, and trade goods from multiple regions, indicate that the town was positioned along significant trade routes connecting northern India to western coastal regions. Yet its physical scale does not align with the level of connectivity suggested by these findings, implying that Vadnagar functioned less as a major destination and more as a node within a wider network, where its stable planning, reliable water systems, and durable construction would have supported consistent long-term operation, effectively functioning as a logistical hub optimized for continuity rather than expansion, a role that further reinforces the idea of intentional system design rather than organic growth. Do you think Vadnagar was simply an advanced ancient town, or evidence of a lost system of engineering knowledge far beyond what we assume? And what is your explanation for this level of precision? Tell me your thoughts in the comments below. Far from the monumental fame of Constantinople or Ravenna, hidden in the hills of southern Serbia, lies a city that seems to defy its own era. Built in the early 6th century under the rule of Justinian I, Karačingrad, widely identified as Justiniana Prima, was not a slow-growing settlement shaped by generations. It was conceived, executed, and completed with a level of urban precision and engineering ambition that suggests something far more deliberate. And yet, within less than a century, possibly closer to 60 or 70 years, it was abandoned. This is the central paradox. A city equipped with fortifications, administrative complexes, multiple basilicas, and most strikingly, a fully integrated hydraulic system capable of sustaining thousands, simply disappears before its systems are truly tested by time. Even more unsettling is this. When compared to other Byzantine settlements of the same period, Karačingrad does not just match them, it surpasses them in planning, clarity, and infrastructural integration. So why did a city built with such foresight fail so quickly? The ruins of Karačingrad were first systematically investigated in the early 20th century, with major excavations beginning in 1912. What initially appeared to be scattered stone remnants soon revealed something far more structured, a carefully organized urban center with defensive walls, street grids, and monumental religious architecture. Over decades of excavation, archaeologists uncovered at least 8 churches, including a large episcopal basilica, a clearly defined acropolis and lower urban zones, streets laid out in near-orthogonal alignment, and evidence of advanced infrastructure beneath the visible ruins. The identification of the site as Justiniana Prima, mentioned in historical texts as a city founded by Emperor Justinian, added a layer of historical grounding. Yet the physical evidence raised more questions than the texts could answer, because while written sources describe its administrative importance, they say almost nothing about the engineering sophistication now visible in the ground. Among all the mysteries of Karačingrad, none is more technically challenging than its water system. The city did not rely on a nearby river or spring, but was instead supplied by an aqueduct system extending several kilometers, channeling water from distant sources into a network of cisterns and distribution channels within the city. At first glance, this resembles earlier Roman achievements, as aqueducts had existed for centuries, but the difference lies in execution. To function properly, an aqueduct must maintain a gradient that is neither too steep nor too shallow, because even a deviation of a few centimeters over long distances can either stall the flow or cause destructive turbulence, and in some Roman systems gradients were maintained at ratios as precise as 1 in 3,000 to 1 in 5,000. At Karačingrad, archaeological measurements suggest similarly controlled slopes, which raises a critical problem, because by the 6th century the Western Roman Empire had already fallen, and although technical continuity existed, large-scale infrastructure projects had become rarer and often less precise. Yet here, in a relatively remote region, engineers achieved stable, long-distance water flow without modern surveying tools, integrated settling tanks and storage cisterns to regulate supply, and created a distribution system capable of serving both public buildings and residential zones. The likely tool for measuring gradients, the Roman chorobates, relied on water levels and plumb lines, and while effective in principle, its precision over several kilometers especially across uneven terrain, is still debated. So the question remains, how did engineers here maintain such accuracy over distance? Was this the survival of Roman engineering tradition at its peak, or evidence that certain practical techniques, never fully documented, were still being applied with surprising mastery? Unlike most ancient cities which evolve organically over centuries, Karačingrad appears to have been built in a single coordinated phase, and its layout reveals a hierarchical zoning system separating religious, administrative, and residential functions, streets intersecting at near right angles, and the strategic placement of gates and towers aligned with internal circulation routes. This is not typical of Byzantine provincial towns, because even in major cities, irregular growth patterns dominate due to earlier foundations and continuous adaptation. A closer comparison would be Roman colonial cities such as Timgad, where grid planning was imposed from the outset. But Karačingrad differs in one key aspect, as its topography is more complex, yet the grid is still maintained with notable consistency. Maintaining orthogonality on uneven terrain requires either significant land modification or advanced surveying techniques capable of projecting geometric plans onto irregular surfaces, and either scenario implies a level of pre-construction planning that goes beyond what is usually documented for the 6th century. The architectural remains of Karačingrad suggest a deep, practical understanding of structural behavior, as walls often employ alternating layers of stone and brick, a technique known to improve flexibility and resistance to cracking, while arches and vaults distribute loads efficiently and column placements reflect an intuitive grasp of weight transfer. Yet this presents a contradiction, because formal structural theory, mathematical descriptions of load, stress, and material limits would not emerge until many centuries later, meaning Byzantine builders relied primarily on experience, tradition, and empirical knowledge. And still, the results at Karačingrad show high levels of symmetry in large basilicas, consistent proportions across multiple buildings, and structural stability that has endured for over 1,400 years. Was this simply the accumulated wisdom of Roman and early Byzantine builders, or does the consistency suggest something more systematic? Perhaps design principles that were never written down but only transmitted through practice? Despite its sophistication, Karačingrad did not endure, as archaeological layers indicate occupation for only a few decades, with abandonment occurring by the late 6th or early 7th century, and there is no single definitive destruction layer pointing to catastrophic collapse. Instead, the evidence suggests gradual decline, followed by relatively rapid desertion, limited signs of prolonged siege or rebuilding, and infrastructure left unused rather than destroyed. This pattern aligns loosely with the broader context of Slavic incursions into the Balkans during the late 6th century. Yet other cities in similar conditions managed to survive, adapt, or relocate, while Karačingrad did none of these and simply ceased to function, which leads to a deeper question. Was the city ever truly sustainable, or was it an imperial project ambitious and symbolically powerful, but ultimately disconnected from the economic and demographic realities needed to maintain it? So what do you think? Was this city a failed experiment, or the last echo of a lost engineering tradition? Share your thoughts in the comments below. In the harsh, semi-arid highlands of the Ores Mountains in modern-day Algeria, far from major rivers and deep within a landscape defined by heat, dust, and scarcity, lies the remains of Lambaesis, once the headquarters of the powerful Legio III of Augusta under the authority of the Roman Empire. At first glance, it appears to be just another Roman military camp, but the deeper archaeologists look, the more one question dominates the site. How did a highly complex, permanently occupied military city, complete with water systems, hospitals, administrative centres, and training academies function for decades in an environment that should not have been able to sustain it at all. Unlike legendary sites lost to myth, Lambaesis was never entirely forgotten, its ruins remaining visible and scattered across the Algerian plateau until systematic study began in the 19th century during French colonial expeditions. Early surveys revealed inscriptions carved into stone blocks, official Latin texts referencing military drills, discipline, and speeches delivered to soldiers, and these unusually detailed records, far more structured than those found at many other Roman sites, immediately suggested that Lambaesis was more than a simple frontier outpost. By the late 19th and early 20th centuries, archaeologists uncovered a carefully organized layout, including a central principia aligned with near-geometric precision, extensive barracks capable of housing thousands of soldiers, a valetudinarium indicating long-term medical infrastructure, and large open courtyards likely used for training and assembly, all pointing toward a permanent and highly disciplined occupation. Later excavations throughout the 20th century expanded this picture even further, revealing road networks extending outward from the camp and connecting it to nearby settlements such as Timgad, suggesting that Lambaesis functioned not in isolation but as part of a broader regional system. Yet with each new layer uncovered, the same contradiction became increasingly difficult to ignore. The infrastructure was too advanced, too permanent, and too dependent on resources for the harsh environment in which it existed. The greatest unresolved mystery of Lambaesis lies beneath its stones in water, because the site preserves evidence of a sophisticated hydraulic system that includes aqueducts channeling water from distant sources potentially spanning tens of kilometers, large underground cisterns coated with waterproof materials such as opus signinum, and an internal distribution network that delivered water across the camp with remarkable efficiency. In a region where annual rainfall is low and evaporation rates are extremely high, sustaining a population of several thousand soldiers would have required an immense and continuous water supply. And when placed into measurable context, the scale becomes even more striking. A Roman legion of approximately 5,000 men, the standard size of units like the Legio III Augusta, would require at least 20 to 30 litres of water per person per day for drinking, cooking, and sanitation, resulting in a daily demand exceeding 100,000 litres, not including water for animals, industrial processes, or inevitable losses through evaporation and leakage. Yet despite this enormous demand, there is no major perennial river located nearby, making the existence of such a system deeply puzzling. Comparisons with other Roman sites only intensify the mystery, because at Vindolanda in Britain, water supply relied on abundant rainfall and nearby streams, while at Carnuntum, proximity to the Danube ensured stable and predictable access. But Lambaesis operated in a marginal environment where such reliability should not have been possible. Several hypotheses attempt to explain this contradiction, including the idea that Roman engineers possessed a far more detailed understanding of regional hydrology than currently documented, allowing them to exploit hidden or seasonal water sources, while others suggest that underground aquifers, perhaps now depleted, once provided more abundant reserves than we see today, and a more controversial theory proposes that the hydraulic system may have been partially inherited or constructed upon earlier undocumented infrastructure. However, even if water could be sourced, maintaining such a system across long distances would require continuous technical oversight to prevent leakage, manage sediment buildup, and ensure consistent flow, meaning that Lambaesis was not merely using water, but actively controlling it in a way that appears disproportionate to both its environmental constraints and the technological assumptions we typically assign to the period. The architectural and epigraphic evidence suggests that Lambaesis functioned as far more than a conventional military base, because inscriptions found on site describe formal speeches delivered by commanding officers that outline discipline, tactical expectations, and organizational hierarchy in a manner resembling institutional doctrine rather than routine operational orders, indicating a level of administrative complexity rarely preserved in other frontier camps. The presence of large assembly halls and carefully structured training spaces further supports the idea that Lambaesis operated as both a training academy and an administrative center, not simply as a place where troops were stationed. While its geographic position near the frontier zones between Roman-controlled territory and desert regions, inhabited by indigenous groups, places it at a strategic but isolated node within the empire's defensive network. This combination of features raises a compelling possibility that Lambaesis may have served as a central command hub coordinating military operations across North Africa, functioning in a role similar to a regional headquarters where strategy, logistics, and communication were organized on a large scale. If this interpretation is correct, then the scale and complexity of the site begin to make sense. Yet it introduces an even deeper question. Why would such a critical command center be established in a location defined by extreme logistical challenges rather than in a more resource-rich and accessible environment? Among the most intriguing discoveries at Lambaesis are its inscriptions, which differ significantly from typical Roman dedicatory or commemorative texts because many of them are highly procedural, detailing military routines, disciplinary systems, and even elements of rhetorical instruction intended for officers and soldiers alike, suggesting a standardized approach to communication and training. However, certain irregularities within these inscriptions have drawn the attention of researchers, including repeated phrasing patterns that deviate from classical Latin syntax, unusual abbreviations that are not widely attested in other regions of the empire, and structural formatting that appears systematic yet remains only partially understood. While some historians interpret these anomalies as local linguistic adaptations or shorthand used within a specific military context, others propose a more speculative interpretation in which these inscriptions may represent early forms of coded or semi-coded communication systems designed to standardize complex information across different units, allowing for more efficient transmission of doctrine and orders. Although there is no definitive evidence that these texts constitute true encryption, the possibility suggests that Lambaesis may have been a site where Roman military organization reached an advanced level of abstraction and systemization that is rarely visible in the archaeological record, hinting at a layer of operational sophistication that remains difficult to fully reconstruct. By the 3rd century CE, Lambaesis began to decline, yet unlike many ancient sites, its transformation does not appear to have been triggered by a single catastrophic event, as there is no clear evidence of widespread destruction, no extensive burn layers, and no definitive signs of sudden abandonment caused by invasion or natural disaster. Instead, the site seems to have undergone a gradual reduction in importance, eventually losing its central role as the Legio III Augusta was disbanded and later reorganized during periods of instability within the Roman Empire, suggesting a slow administrative shift rather than a violent collapse. Even so, this explanation does not fully resolve the mystery, because if Lambaesis depended heavily on its complex water system, any disruption, whether technical, environmental, or political, could have had cascading effects on its ability to function. Yet no single cause has been definitively identified, leaving the site's decline as ambiguous as its rise. When each component of Lambaesis is examined individually, it can be explained within the known capabilities of Roman engineering and military organization, including advanced construction techniques, efficient logistical planning, and strategic territorial control. Yet when all these elements are considered together, the site presents a paradox in which a large, permanent, and resource-intensive military complex not only existed, but operated successfully within an environment that should have imposed severe limitations on its sustainability. Compared to other Roman sites, Lambaesis does not necessarily exceed the technical limits of the empire, but it applies those capabilities in a context where they seem least viable, making it stand out as a case where known technology was pushed into conditions that challenge our assumptions about its practical application. Do you think Lambaesis was simply the result of Roman engineering at its peak, or could it be evidence of knowledge we still don't fully understand? Share your thoughts in the comments below. Deep in the mountains of northeastern Algeria, far from the coastlines that once powered the Roman Empire, the ruins of Cuicul rise from stone valleys with a contradiction that still unsettles archaeologists today. The city, now known as Jamila, was never built where a Roman city was supposed to exist. It stood nearly 3,000 feet above sea level, surrounded by steep ridges, fractured terrain, freezing winters, and difficult supply routes. There were no major ports nearby, no enormous rivers feeding trade, and no obvious strategic reason to construct one of the most sophisticated urban centers in Roman North Africa in such an isolated environment. Yet the Romans did not merely settle here. They engineered aqueducts across broken mountainsides, carved theatres into unstable slopes, expanded massive forums beyond practical necessity, and covered the region with an urban complexity that should not logically exist in terrain like this. Even stranger, the city later expanded into something larger and more ambitious just before slowly fading into silence without evidence of catastrophic destruction. Cuicul was not destroyed like Pompeii. It was abandoned gradually, as if an enormous project had simply lost its purpose. And that raises the central mystery surrounding the city today. Why did Rome invest so much engineering, manpower, and architectural precision into a place that appears fundamentally irrational? The ruins were first systematically studied during the 19th century after French expeditions moved deeper into Algeria during the colonial period. What they discovered beneath layers of soil and vegetation shocked European archaeologists because the city was extraordinarily well preserved. Massive colonnaded streets still followed the contours of the mountains. Temples, baths, basilicas, markets, and elite houses survived in remarkable condition. Archaeologists quickly realized that Cuicul was not a small frontier settlement. It was a fully developed Roman city constructed with expensive urban planning principles usually reserved for economically vital regions of the empire. Excavations revealed inscriptions dating the city's formal founding to around 96 CE under Emperor Nerva. Later editions connected to the reigns of emperors such as Caracalla demonstrated that the city remained politically important for centuries. But the deeper excavations went, the stranger the urban logic became. Most Roman colonial cities followed an efficient geometric system. Cities such as Timgad were designed with near-perfect orthogonal street grids because flat terrain allowed Roman engineers to maximize movement, drainage, military organization, and administrative control. Cuicul breaks that pattern almost immediately. Instead of adapting the terrain to Roman urbanism, the Romans adapted Roman urbanism to the terrain itself. Streets bend unexpectedly. Major civic buildings sit on awkward elevations. Entire districts appear compressed into irregular platforms cut directly into mountain rock. The Forum does not dominate the city with the same clean symmetry seen elsewhere in the empire. Instead, the architecture appears forced into compromise after compromise. This has led some historians to describe Cuicul as one of the clearest examples of topographic urbanism in the Roman world. where engineering had to negotiate constantly with hostile geography. But this explanation creates another problem. Why choose such a hostile site at all? The mystery becomes more intense when examining the city's hydraulic systems. Roman civilization depended on water engineering. Cities without stable water access rarely expanded into large urban centers because public baths, fountains, sewage systems, and agriculture required enormous hydraulic reliability. Yet Cuicul existed in a mountainous region without major nearby rivers capable of naturally sustaining large-scale urban growth. Despite this, archaeologists uncovered sophisticated aqueduct systems transporting water across difficult elevations. Reservoirs and cisterns stored enormous quantities of water, while bath complexes consumed levels of hydraulic infrastructure that appear excessive for a relatively isolated inland city. Some estimates suggest Roman public baths could consume hundreds of thousands of liters of water daily, depending on scale and population density. In Cuicul, the existence of multiple bathing complexes suggests planners anticipated either a significantly larger population or a long-term urban expansion strategy that never fully materialized. This raises one of the city's greatest unanswered questions. Was Cuicul originally intended to become something much larger than what history ultimately remembers? The scale of later construction strongly suggests ambition beyond normal provincial administration. During the 2nd and 3rd centuries CE, the city underwent major expansion. New forums were added, monumental arches appeared, elite residential districts expanded outward into increasingly difficult terrain. Archaeologists discovered evidence that sections of the city required large-scale terracing simply to create enough stable surface area for construction. This was not cheap engineering. Roman labor systems could move enormous quantities of stone and earth, but such projects were usually concentrated in economically strategic cities tied to trade networks or imperial politics. Cuicul sat far from the Mediterranean coast and lacked the commercial intensity of cities like Carthage. Yet its architecture increasingly resembled cities of higher imperial significance. Some scholars believe the answer may lie in Roman control strategies across North Africa. During the 1st centuries CE, Rome viewed North Africa as one of the empire's agricultural foundations. Grain production from the region fed millions, including large parts of Rome itself. Inland cities may have functioned not merely as trade centers, but as administrative anchors stabilizing difficult tribal territories beyond the coastal zones. Cuicul's mountainous position may therefore have offered strategic oversight over interior movement routes and local populations. But even this explanation feels incomplete because the city's sophistication exceeds what would normally be required for military supervision alone. Another unsettling feature of Cuicul is the apparent contradiction between environmental limitation and urban confidence. Winters in the region can become unexpectedly cold due to elevation, while summers remain dry and difficult. Agriculture in mountainous terrain is inherently less efficient than farming on lowland plains. Transporting construction material through steep valleys would have required enormous logistical coordination. Every column, every block of carved limestone, every decorative element had to cross terrain that naturally resisted urbanization. Some Roman ruins elsewhere in North Africa display signs of practical compromise. Cuicul instead displays repeated evidence of architectural ambition overcoming environmental logic. The theatre is one of the clearest examples. Roman theatres were usually positioned to take advantage of natural slopes, reducing construction costs by embedding seating into hillsides. Cuicul's theatre follows this principle partially, but the terrain surrounding it remained difficult enough that additional structural adaptation became necessary. The engineering precision required to stabilize large public structures on uneven terrain would have demanded highly skilled surveyors and labor specialists. Roman engineering manuals describe sophisticated leveling techniques using water channels, measuring rods, and geometric calculations. But Cuicul demonstrates those principles applied in terrain where errors could trigger collapse or long-term instability. Even today, parts of the city seem improbably balanced against the mountains themselves. Then, there is the question of population. Archaeologists estimate that Cuicul may have housed somewhere between 10,000 and 20,000 inhabitants at its peak, depending on the expansion phase considered. For comparison, many Roman frontier settlements remained far smaller throughout their existence. Supporting such a population in elevated terrain would have required stable food supply chains, extensive local agriculture, and long-term political security. Yet the archaeological record does not fully explain how the city maintained such complexity for centuries. Some historians argue that North Africa during Roman rule was wealthier and more urbanized than many people realize today. This is true, but Cuicul still stands out even within that context because of the mismatch between geography and ambition. Religious transformation inside the city adds another layer of mystery. During the later Roman Empire, Christianity spread through the region and began reshaping urban identity. Basilicas appeared. Pagan temples declined. New religious architecture emerged inside older civic frameworks. But unlike some Roman cities violently destroyed during periods of religious upheaval or invasion, Cuicul appears to have transitioned gradually. Archaeological evidence suggests continuity rather than catastrophic collapse. Streets remained in use, buildings were repurposed, urban life slowly contracted instead of exploding into destruction. This gradual decline makes the city strangely difficult to explain because there is no singular disaster to account for its disappearance. Climate may have played a role. Some paleoclimate studies suggest portions of North Africa experienced increasing aridity during late antiquity. Reduced agricultural reliability could have weakened inland cities dependent on fragile regional economies. Trade routes may also have shifted toward more stable coastal systems. Political fragmentation following the weakening of Roman authority almost certainly affected inland administration. Yet none of these factors fully explain why Rome invested so heavily in Cuicul in the first place. What do you think Cuicul truly was, a strategic Roman experiment, an unfinished imperial dream, or something far more mysterious? Share your thoughts in the comments below. The site of Zominthos was not uncovered as a grand, obvious ruin rising from the landscape. Instead, it emerged gradually from beneath layers of soil and collapsed stone during systematic excavations initiated in the 1980s by Greek archaeologist Yannis Sakellarakis. Located on the slopes of Mount Ida in central Crete, at an elevation approaching 1,200 meters above sea level, the site immediately challenged established assumptions about the spatial logic of the Minoan civilization. Early excavation campaigns revealed a surprisingly extensive architectural footprint. What began as a small exposed structure expanded into a complex exceeding 50 rooms, arranged along organized corridors and axes rather than random accretion. Subsequent seasons uncovered evidence of multiple construction phases, suggesting long-term occupation rather than temporary use. Stone walls preserved to significant heights indicated that the building once rose to at least 2, possibly 3 stories, an extraordinary feature given both the era and the environmental constraints. Artifacts recovered from different excavation layers further complicated interpretation. Large storage vessels, known as pithoi, implied surplus accumulation. Loom weights pointed to textile production. Fine ceramics, tools, and ritual objects suggested a hybrid space neither purely domestic nor purely ceremonial. Unlike lowland centers such as Knossos, which are clearly embedded in agricultural and maritime networks, Zominthos appeared isolated, yet functionally sophisticated. Each excavation phase added detail but not clarity. Instead of resolving its purpose, the site deepened the central question: Why construct such a complex system at an altitude where environmental pressures are significantly higher and logistical access is severely limited? The architectural features of Zominthos reveal a level of planning that contradicts its geographic context. The terrain of Mount Ida is not naturally suited for large-scale construction. Slopes are uneven, soil stability varies, and exposure to wind and seasonal temperature fluctuations increases structural stress. Yet the builders created a stable, load-bearing complex with thick stone walls and carefully aligned rooms. Archaeological measurements show that some wall segments exceed 1 meter in thickness, indicating intentional design for vertical load distribution. This aligns with the hypothesis of multi-story construction, supported by stair remnants and collapsed upper-level materials. The precision of stone fitting, while not as finely cut as later classical masonry, still demonstrates controlled shaping and placement, minimizing structural gaps. Comparatively, other Bronze Age structures at similar technological levels rarely exhibit this combination of elevation, scale, and complexity. In Mesopotamia, for instance, urban centers such as developed horizontally across flat floodplains. In Egypt, monumental architecture like pyramids relied on river transport systems for material movement and logistical support. Zominthos, by contrast, lacks both flat terrain and navigable water systems. This suggests that the builders possessed not only technical knowledge of construction mechanics, but also a willingness to apply it in conditions where the cost-to-benefit ratio appears unfavorable. The question is not whether they could build such a structure, but why they chose to do so here. The internal evidence from Zominthos resists simple classification. Textile production indicators, including loom weights and spindle whirls, point toward organized manufacturing activity. Storage containers suggest accumulation and redistribution of goods. Yet spatial layouts, particularly larger central rooms and symmetrical arrangements, mirror patterns associated with ceremonial or administrative functions. The proximity to Mount Ida adds another layer of interpretation. In Minoan belief systems, high-altitude locations were often linked to religious practices, and the mountain itself is associated in later Greek mythology with the upbringing of Zeus. This raises the possibility that Zominthos functioned as a ritual center integrated with economic activity. However, combining production and ritual at this scale in a remote environment introduces logistical contradictions. Production centers typically require efficient access to raw materials and distribution routes. Ritual centers, while sometimes remote, do not usually maintain extensive industrial infrastructure. Zominthos appears to operate as a hybrid system, one that integrates economic, symbolic, and possibly administrative roles. Such a model does not fully align with known Minoan site typologies, suggesting either a specialized function or a broader organizational framework that remains poorly understood. Among all unresolved questions, the problem of transportation stands as the most technically challenging. Constructing a multi-room, multi-story stone complex at an elevation of approximately 1,200 meters would have required the consistent movement of heavy materials over steep and uneven terrain. To estimate the scale of this challenge, consider that even a modest stone block weighing 200 to 500 kilograms would require coordinated labor to transport uphill. If the structure contains hundreds or thousands of such stones, the cumulative logistical effort becomes enormous. Unlike Egyptian construction, where the Nile provided a low-friction transport corridor, or Mesopotamian cities built near resource zones, Zominthos offers no obvious natural advantage. No clear archaeological evidence has yet confirmed the existence of engineered roads leading directly to the site. This absence is critical. In other ancient contexts, such as Roman mountain routes, even minimal infrastructure leaves detectable traces, graded paths, retaining walls, or compacted surfaces. At Zominthos, such features remain either undiscovered or ambiguous. Several hypotheses attempt to address this gap. One possibility is the use of seasonal transport strategies. During colder months, harder ground conditions or even limited snow cover could reduce friction, allowing sled-like movement of materials. However, this would require precise timing and coordination, as well as knowledge of seasonal environmental behavior. Another hypothesis involves distributed labor networks. Rather than transporting large stones in single movements, smaller components could have been moved incrementally and assembled on site. Yet this contradicts the presence of larger structural blocks that appear integral rather than composite. A third possibility is the existence of ancient mountain pathways that have since eroded or been obscured by geological processes. Crete is tectonically active, and erosion over thousands of years could erase surface evidence of infrastructure. If such routes existed, they would imply a broader network of high-altitude movement than currently documented. Experimental archaeology provides some comparative context. Studies on stone transport in pre-industrial societies suggest that teams of 10 to 20 individuals can move loads of several hundred kilograms over short distances using ropes, wooden sleds, and rollers. However, scaling this up to sustained operations across steep gradients introduces exponential increases in difficulty. The transportation problem at Zominthos is not merely a question of effort. It is a question of system design. It implies planning, resource allocation, and possibly technological adaptations that have left minimal trace. In this sense, the absence of evidence becomes part of the mystery itself. If a complex like Zominthos required this level of planning, labor, and engineering in such an inhospitable location, what was important enough to justify it? And more importantly, what kind of system could sustain it? Leave your thoughts in the comments below. Rajgir is located in the state of Bihar, northeastern India, sitting inside a natural basin surrounded by 5 hills. The site has been known in ancient texts for over 2,000 years, particularly in Buddhist and Jain records. But the true scale of its fortification system only became clear through systematic surveys during the 19th and 20th centuries. Early documentation by surveyors of the Archaeological Survey of India revealed that what appeared to be scattered stone remnants were actually part of a continuous defensive network stretching over 40 kilometers. Later field studies in the mid-20th century mapped the walls in detail, identifying multiple construction phases and confirming their antiquity to around the 6th century BCE, corresponding to the rise of the Kingdom of Magadha. Excavations conducted in different sectors of Rajgir did not uncover a single centralized construction event. Instead, archaeologists found layered occupation evidence. Azim, in some areas, pottery fragments dated to the northern black polished ware phase, roughly 7th to 3rd century BCE, were discovered near the wall bases, suggesting early urban activity linked to the fortifications. Other trenches revealed later repairs, with smaller stones inserted between larger blocks, indicating that the structure was maintained across generations rather than built once and abandoned. At certain hill passes, researchers identified gate-like constrictions where the wall narrows and thickens simultaneously, implying controlled entry points, though no complete gate structures survived. These findings collectively suggest that Rajgir was not a static monument, but an evolving system integrated into a living landscape. Yet even with these discoveries, the fundamental question remained unchanged. Why construct such an enormous wall system in this specific way? Most ancient fortified cities followed a clear defensive logic. Walls enclosed a compact urban core, minimizing perimeter length while maximizing protection. This principle can be observed in Mesopotamian cities like Ur, where walls were tightly constructed around dense habitation zones, or even in later large-scale systems like the Great Wall of China, which followed strategic corridors rather than enclosing vast terrain indiscriminately. Rajgir does the opposite. Its walls expand outward, embracing not just settlements but entire hills, valleys, and empty stretches of land. The enclosed area is far larger than what would be necessary to protect a population center of the time. Based on comparative estimates, a 6th century BCE urban population in the region would not have required a perimeter exceeding a few kilometers. Rajgir exceeds that by an order of magnitude. This creates a measurable contradiction. If the wall length is approximately 40 kilometers, and the average height is estimated between 4 to 5 meters, the total construction volume would reach hundreds of thousands of cubic meters of stone. For a society without iron tools in widespread use and without advanced transport systems, the labor investment would have been enormous. Yet the return, in purely defensive terms, appears inefficient. This imbalance between effort and function suggests that defense alone cannot fully explain the system. The walls are built using what is classified as Cyclopean masonry, large irregular stones stacked without mortar. Unlike the polygonal perfection seen in Saxe-Heuneburg, where stones are cut to interlock with near microscopic precision, Rajgir's stones are comparatively rough. However, they are not randomly placed. Field observations show that stones are selected and positioned to distribute weight effectively, with smaller stones filling gaps to stabilize the structure. A comparison with Mycenaean Greece reveals a key difference. Mycenaean Cyclopean walls often use massive blocks with limited shaping, relying on sheer weight for stability. Rajgir, by contrast, uses a hybrid approach. Medium to large stones arranged in a way that balances mass and interlocking friction. This suggests an understanding of structural stability that does not rely on perfect cutting but on controlled irregularity. From an engineering perspective, this is significant. Modern dry stone construction principles recognize that slight irregularities can improve resilience, especially in seismic or high erosion environments. The microgaps allow for drainage, reducing hydrostatic pressure buildup. In regions with seasonal monsoon patterns like Bihar, this could explain why the walls have survived for over 2,000 years while more refined masonry elsewhere deteriorated. The paradox is clear. A seemingly primitive technique produces a long-term durability that aligns with advanced engineering logic. One of the least understood aspects of the Rajgir walls is not how they were assembled, but how the materials were moved. Geological surveys indicate that many stones used in the walls were locally sourced, but local in this context still means distances of several hundred meters to several kilometers across uneven terrain. Experimental archaeology provides rough estimates. Moving a stone weighing 500 kilograms across flat ground using wooden sledges might require 10 to 20 individuals. On an incline, especially without mechanical advantage systems, the required force increases dramatically. If even a fraction of the stones used in Rajgir fall within this weight range, the total labor investment would scale into tens of thousands of person days. Unlike Egyptian pyramid construction, where clear evidence of ramps and organized labor systems exists, Rajgir offers no visible remains of transport infrastructure. No preserved ramps, no carved pathways, no anchor points for pulley systems have been definitively identified. This absence creates a gap between what must have happened and what can be observed. The stones are there, the terrain is difficult, the intermediate steps are missing. Another unresolved aspect is the relationship between the walls and the surrounding hills. At first glance, the builders appear to use the hills as natural defenses, connecting ridgelines to form a continuous barrier. However, detailed mapping shows multiple segments where the wall diverges from the most efficient route. Instead of following the shortest path between two defensible points, the wall sometimes descends into valleys or climbs steeper slopes than necessary. From a purely military standpoint, this is counterintuitive. Shorter walls are easier to defend and maintain. Longer, more complex routes increase vulnerability. This suggests that the layout may have been influenced by factors beyond defense. Possibilities include territorial demarcation, ritual boundaries, or even control over movement patterns within the landscape. In a region associated with early Buddhism and Jainism traditions, spatial organization may have held symbolic meaning not immediately visible in the archaeological record. The wall, in this interpretation, becomes not just a barrier, but a framework defining how space itself was understood. The most measurable anomaly remains the wall's survival. Structures built without mortar are typically vulnerable to weathering, especially in climates with heavy rainfall and temperature variation. Yet large sections of the Rajgir walls remain intact after more than 2 millennia. Comparative studies show that mortar-based constructions in similar environments often degrade faster due to water infiltration and chemical breakdown. Dry stone systems, when properly constructed, can adapt to minor shifts without catastrophic failure. Rajgir appears to exploit this principle at a large scale. If the walls have indeed stood for over 2,500 years, they represent a long-term performance benchmark that rivals or exceeds many later constructions. This challenges the assumption that technological advancement always produces superior durability. So what do you think, was this truly a defensive system, or something far more complex that we still don't understand? Share your thoughts in the comments below. Fragments came first, not a dramatic excavation, but scattered stones, unusual carvings, and quiet reports from the outskirts of Aix-en-Provence in the early 19th century, all hinting at something older buried beneath the Provençal landscape. By the 1840s, systematic observations began to identify the plateau. As more than a ruin, it was an oppidum, a fortified urban centre belonging to the Salians, a powerful Celtic Ligurian confederation active during the 2nd and 1st centuries BCE. Yet it was not until the early 20th century, particularly between the 1920s and 1940s, that controlled excavations began revealing the true scale of the site. Uncovering defensive walls stretching over 300 meters, organized residential blocks, workshops, and central plazas, while carbon dating and artifact typology placed the main occupation between roughly 180 and 120 BCE, aligning with the final phase of Salians' power before Roman intervention. And even in these early excavations, something did not align with expectations, because Entremont was structurally coherent, but culturally anomalous. Across multiple excavation campaigns, 1920s, 1950s, and again in the late 20th century, researchers documented a settlement that was surprisingly advanced for its context. With stone-built houses arranged in semi-regular blocks, streets with defined pathways suggesting planned urban organization, storage facilities capable of holding significant agricultural surplus, and clear evidence of metallurgy, including iron tools and weapon fragments. Comparatively, other Celtic oppida such as Bibracta or Manching oppidum demonstrate large-scale urban planning and trade networks, with population estimates reaching several thousands. Yet, Entremont differs in one crucial aspect: its symbolic density, because where Bibracta reveals economic infrastructure and Manching reflects proto-industrial production, Entremont appears disproportionately focused on ritualized spaces and sculptural installations, an imbalance that immediately suggests the site was designed for something beyond simple habitation. Among the most disturbing and scientifically debated discoveries at Entremont are the sculpted heads, with dozens of stone carvings, many life-sized, found embedded in walls, placed within niches or integrated into pillar structures, while several pillars contain cavities shaped precisely to hold human skulls, and in some cases, cut marks on actual human remains found nearby suggest decapitation shortly after death, consistent with ritual processing. Although the so-called Celtic head cult is not unique to Entremont, with classical sources including accounts attributed to Diodorus Siculus, describing Gaulish warriors preserving the heads of enemies as trophies, the level of systematic replication here exceeds simple trophy display because the heads are carved with consistent proportions, suggesting standardized measurement systems, while facial features show individual variation implying possible portraiture rather than symbolic abstraction, and the repetition of specific configurations heads aligned along axes or arranged in symmetrical clusters indicates intentional spatial encoding, leading some researchers to propose that these heads may represent lineage markers, social hierarchy, or even mnemonic devices, functioning as an early form of visual data storage tied to identity and power, which, if accurate, would transform Entremont from a ritual site into a structured, symbolic system that has not yet been decoded. At first glance, Entremont appears to function as a fortified settlement, with its elevated position, stone ramparts, and controlled access points suggesting defensive intent, yet closer analysis reveals inconsistencies that challenge this assumption. Because wall thickness averages between 2 and 3 meters, sufficient against small-scale raids, but inadequate against organized Roman siege tactics. While there is no clear evidence of advanced defensive features, such as towers optimized for projectile coverage, and central areas occupy disproportionately large open spaces that reduce defensive density. In contrast, oppida like Manching exhibit complex gate systems, defensive ditches, and layered fortifications, making Entremont appear under-engineered for its geopolitical context, which raises the critical question of whether it was ever designed primarily for defense at all, or whether it functioned instead as a ceremonial political center, where architecture served to stage power rather than protect it, especially given that the alignment of plazas, pillars, and sculptural installations suggests a form of spatial choreography, an environment designed to guide movement, attention, and perception in a controlled and possibly ritualized manner. Historical records confirm that in approximately 123 BCE, Roman forces, led by Gaius Sextius Calvinus, defeated the Salians and established the nearby settlement of Aquae Sextiae. Yet the archaeological signature at Entremont complicates this narrative because typical conquest layers would include extensive burn strata, scattered weaponry, and mass burial evidence, whereas at Entremont findings are far more ambiguous, with limited burn evidence that is localized rather than widespread, objects left in situ including tools and domestic items, and an absence of large-scale massacre indicators, a pattern that aligns more closely with rapid but organized abandonment than chaotic destruction. This has led to multiple interpretations, ranging from forced relocation to strategic withdrawal, and even more controversial hypotheses suggesting that certain structures, particularly those containing symbolic elements, were deliberately decommissioned or neutralized, implying that the fall of Entremont may not have been purely military, but may instead represent the suppression of a cultural system that the Romans did not or could not integrate. The final layer of the mystery lies in the craftsmanship itself, as detailed analysis of the carvings shows consistent depth and curvature across multiple sculptures, repeated geometric relationships between facial features, and surface finishing techniques that suggest controlled abrasion rather than random chipping. While experimental archaeology indicates that achieving such precision with iron tools alone would require significant time investment and a high degree of skill standardization, yet the sheer volume of carvings suggests production beyond isolated artisan work. When compared to Mediterranean cultures such as the Greeks, who developed formalized proportional systems like the canon of Polykletos to standardize sculpture, the absence of any documented equivalent among the Salians becomes striking because despite the lack of written evidence, the output at Entremont implies the existence of an implicit technical framework, a knowledge system, transmitted through practice rather than text, raising the possibility that what we see today is only the visible result of a deeper, undocumented methodology. What do you think were the stone heads at Entremont ritual trophies, or part of a structured system we no longer understand? Share your perspective below. On the northwestern coast of Libya, facing the blue waters of the Mediterranean Sea, the ruins of Sabratha rise from the sand with a level of precision that feels deeply unsettling. Columns still stand in near-perfect alignment. Underground drainage systems continue to function after more than 15 centuries. And inside collapsed villas and temples, thousands of microscopic stone fragments still form images so detailed that archaeologists sometimes compare them to paintings rather than mosaics. Sabratha is usually introduced as a Roman trade city, but that explanation feels incomplete the moment you begin looking closely at the engineering hidden beneath the ruins. Because this was not simply a wealthy coastal settlement, it was a city constructed with an obsessive degree of organization, mathematical balance, and technical refinement that appears strangely disproportionate to the tools officially available at the time. What makes Sabratha disturbing is not one isolated mystery, it is the accumulation of them. The city was first established by Phoenician traders around the 6th century BCE, before later becoming part of the Roman world. Its location made it strategically valuable, positioned between the Mediterranean trade network and caravan routes leading deep into Africa. Yet the modern rediscovery of Sabratha came slowly. For centuries, much of the city remained buried beneath wind-blown sand after earthquakes and abandonment, gradually erased it from view. Major excavations accelerated during the Italian archaeological campaigns of the 1920s and 1930s, revealing theatres, baths, forums, temples, villas, ports, and extensive mosaics preserved in astonishing condition. But the more archaeologists uncovered, the stranger the city became. Unlike many ancient settlements that grew chaotically over time, Sabratha appears unnervingly organized. Streets intersect at calculated angles. Public spaces align with civic structures in ways that maximize movement and visibility. Water systems were integrated directly beneath transportation routes. Even today, satellite analysis shows sections of the urban layout maintaining geometric consistency over surprisingly large areas. Some Roman cities demonstrate planning. Sabratha demonstrates systemization. And nowhere is that systemization more visible than in its theatre. The Roman theatre of Sabratha is often described as one of the best preserved theatres from the ancient world. But preservation alone is not what shocks specialists. It is the complexity of the structure itself. The stage facade rises nearly 3 stories high, covered in marble columns and sculptural decoration arranged with such symmetry that even minor deviations become immediately visible to the human eye. The structure contains an intricate network of backstage corridors, elevated passages, hidden chambers, and acoustic surfaces carefully positioned to project sound toward thousands of spectators. Modern acoustic studies of Roman theatres have shown that some could amplify speech with remarkable efficiency despite lacking electronic enhancement. Yet Sabratha appears to operate at an even higher level of refinement. Researchers analysing comparable Roman theatres found that certain seating geometries naturally reinforced vocal frequencies between roughly 500 and 2000 Hz. Precisely the range most important for human speech. Clarity. At Sabratha, the curvature of the cavea and the placement of architectural surfaces suggest intentional acoustic optimization rather than accidental success. That creates a deeply uncomfortable question. Did Roman architects truly achieve this level of acoustic engineering entirely through empirical trial and error? Or were they operating with mathematical principles that are only partially understood today? Because Sabratha repeatedly crosses the line between practical construction and excessive precision, the city's hydraulic systems reveal the same pattern. Excavations uncovered underground drainage networks, built with carefully controlled gradients that allowed wastewater and runoff to move efficiently across large sections of the city without stagnation. Even slight errors in slope would have caused flooding or blockages, yet many channels maintained functional flow dynamics across long distances. Roman engineers are often celebrated for aqueducts and water management, but Sabratha presents an additional mystery: environmental contradiction. The city existed on a coastline vulnerable to salt corrosion, shifting sand, seasonal storms, and seismic instability. Under those conditions, maintaining long-term hydraulic integrity should have been extraordinarily difficult, and yet portions of the system survived for centuries. Comparisons with other Roman coastal cities make the anomaly even sharper. In some Mediterranean settlements, water systems degraded rapidly once maintenance collapsed. But parts of Sabratha's infrastructure endured despite earthquakes and abandonment. Archaeologists studying Roman concrete have discovered that certain ancient marine mixtures reacted chemically with seawater to strengthen over time through mineral crystallization. Samples from Roman maritime structures elsewhere in the Mediterranean revealed formations of aluminum tobermorite, a rare mineral associated with long-term durability. The implication is astonishing. Some Roman builders may have accidentally or intentionally created materials capable of outperforming aspects of modern coastal concrete in longevity. This is where Sabratha stops feeling merely advanced and begins feeling almost impossible. Ancient mosaics are common throughout the Roman world, but the mosaics of Sabratha possess a level of detail that repeatedly forces historians into uncomfortable comparisons with later artistic traditions. Some floors contain tesserae, the tiny stone pieces forming the image cut so small and placed so densely that transitions between color tones appear smooth to the naked eye. In certain sections, shadows, muscle contours, folds of fabric, and facial expressions emerge with astonishing realism. The problem is scale. Many tesserae measure only a few millimeters across. Producing thousands upon thousands of uniform fragments by hand would already require enormous labor. But arranging them with such precision across large surfaces introduces another problem entirely: error accumulation. Even microscopic alignment mistakes compound over distance. Yet, numerous mosaics maintain geometric consistency and visual proportionality across entire rooms. Some archaeologists estimate that highly detailed Roman mosaics could require millions of individual tesserae and years of labor. But labor alone does not explain the precision. The artisans had no magnification devices comparable to modern optical tools, no laser alignment systems, no modern adhesives. And yet some compositions demonstrate spacing control so accurate that the eye struggles to detect irregularity even after nearly 2,000 years. One mosaic in particular continues to attract fascination because of its illusionistic depth. Human figures appear almost volumetric under angled light. The effect resembles techniques associated with Renaissance painting more than traditional floor decoration. Scholars usually attribute this to extraordinary craftsmanship. But that answer sometimes feels too convenient, because the question is not whether skilled artists existed. The question is how such consistency was maintained physically across enormous surfaces without modern precision instruments. And Sabratha is not isolated in this phenomenon. Similar high-detail mosaics appear in places like Pompeii and Antioch, but Sabratha stands apart for the density of preservation and the environmental conditions under which those works survived. Heat, salt air, earthquakes, moisture fluctuations, and centuries of abandonment should have destroyed much of this detail. Yet many sections remained intact beneath the sand like sealed time capsules. That preservation introduces another unresolved mystery. Why was the city abandoned so completely in the first place? Historical records mention earthquakes during the 4th century CE, economic decline, Vandal invasions, and Byzantine reconquest, all likely contributed to instability. But no single event fully explains the city's gradual disappearance from major historical relevance. Trade cities rarely vanish cleanly. Strategic ports are usually reoccupied, rebuilt, or absorbed into later systems. Sabratha instead faded into silence. Even more strangely, many monumental structures were not systematically dismantled for material reuse at the scale historians would expect. In numerous ancient cities, stone blocks were stripped aggressively over centuries by later populations. At Sabratha, parts of the urban landscape remained eerily frozen beneath layers of sand and collapse. It is almost as if the city was interrupted rather than conclusively destroyed. What do you think Sabratha truly represents? A forgotten peak of ancient human knowledge, or evidence that parts of history may have been far more advanced than we realize? Share your thoughts in the comments section below. The site now known as Candi Sukuh was not discovered in the modern sense. It was never entirely lost. Local communities on the slopes of Mount Lawu had long known of its existence, but it was not until the early 19th century, during the British administration of Java under Thomas Stamford Raffles, that the structure entered formal historical record, when in 1815 surveyors documented a stepped stone structure unlike any other in Java, noting its unusual geometry and explicit carvings. And this marked the beginning of its transition from local sacred site to archaeological subject. Systematic archaeological work followed in the early 20th century under the Dutch East Indies Archaeological Service, with excavations between the 1910s and 1930s revealing multiple terraces, fragmented statues, and a series of relief panels carved directly into andesite blocks, while later restoration campaigns in the 1970s and 1980s reconstructed parts of the main pyramid and uncovered additional artifacts such as ritual platforms, drainage channels, and dislodged linga yoni sculptures. And what made each phase of excavation unusual was not the sheer volume of material recovered, but its inconsistency with known design norms of the Majapahit Empire. Since most late Majapahit temples followed symmetrical mandala layouts with intricate bas-reliefs, whereas Suku's layout appeared asymmetrical, its carvings minimalistic yet symbolically dense, and its central structure, a truncated pyramid rising approximately 15 meters, composed of roughly cut but tightly fitted andesite blocks, and radiocarbon dating of associated organic remains, together with stylistic analysis of inscriptions, places the site firmly in the 15th century, making it one of the last major religious constructions before the decline of Majapahit. Yet paradoxically, its design seems to look backward or perhaps sideways toward a completely different architectural logic that does not align with the trajectory of Javanese temple evolution. The most striking feature of Candi Sukuh is its resemblance to step pyramids found in Mesoamerican pyramids, such as those at Chichén Itzá. And this resemblance is not superficial because both structures exhibit stepped terraces, rising and receding layers, a central staircase aligned with the main axis, and a truncated summit platform rather than a pointed spire. Yet the comparison immediately introduces contradictions, since there is no credible evidence of transoceanic contact between Java and Mesoamerica in the 15th century, and the mathematical precision differs significantly, with the pyramid of Chichén Itzá encoding calendrical information such as 365 steps corresponding to the solar year. While Sukuh's steps do not follow any known numerical cosmology, and yet Sukuh's geometry is clearly not random because measurements indicate that the incline angles of its staircases fall within a narrow ergonomic range of roughly 30 to 35 degrees optimized for human ascent, while the terraces are proportioned with a consistency that implies deliberate planning, even if not aligned with classical Javanese canons, leading to a deeper question that moves beyond diffusion theories into independent convergence, where two distant civilizations may have arrived at similar structural solutions for ritual elevation, and if that is the case, then the real mystery becomes why the builders of Majapahit, who possessed highly developed architectural knowledge, would abandon their own established system in favor of a form that appears alien to their cultural and technological lineage. At first glance, the stonework of Candi Sukuh appears crude, especially when compared to the finely polished surfaces of Borobudur, as Sukuh's blocks are irregular with visible tool marks and uneven faces, a feature often interpreted as evidence of declining craftsmanship in the late Majapahit period. Yet detailed surveys reveal a more complex reality, in which laser scanning and structural analysis demonstrate that many of the blocks fit together with minimal gaps, often measuring less than a few millimeters. A level of precision that is difficult to achieve using simple iron chisels, particularly when working with andesite, a dense volcanic rock with a Mohs hardness of approximately 6, and experimental archaeology indicates that shaping such material with period tools would require prolonged and controlled effort. Yet the surfaces at Sukuh do not display the expected iterative chipping patterns associated with such labor-intensive processes, and the paradox deepens when considering the transport and placement of larger stones, some weighing several hundred kilograms and positioned on upper terraces where access is constrained, with no clear evidence of ramps or lifting systems having been identified, unlike at Borobudur, where large-scale coordinated labor and earthen ramp systems are inferred, and this creates a contradiction in which a structure that appears visually rough is, in fact, structurally precise, suggesting a construction approach that prioritizes function and fit over surface refinement, implying either a different technological methodology or a different set of priorities that remain poorly understood. The reliefs of Candi Sukuh are among the most controversial in Southeast Asian archaeology, dominated by explicit depictions of linga and yoni that represent male and female generative forces in Hindu cosmology. Yet what distinguishes Sukuh is not the presence of these symbols but their scale, placement, and directness. As a large linga sculpture, once standing upright, dominates the central axis, while surrounding panels depict human figures and anatomical details with unusual clarity, leading some scholars to interpret the site as a fertility temple, possibly linked to initiation rituals or agricultural cycles. But alternative interpretations suggest a more structured symbolic system in which the arrangement of carvings follows a deliberate spatial logic, with certain panels aligned along processional paths suggesting narrative sequencing, and others positioned at transitional points between terraces, indicating stages in a ritual ascent. And some researchers propose that these carvings function as a symbolic map of transformation from the physical to the spiritual or from life to regeneration. While more speculative theories argue for encoded knowledge embedded in the proportional exaggeration and repetition of anatomical forms, comparing them to schematic representations rather than purely artistic expressions. And although there is no direct evidence of biological instruction, the consistency and placement of these motifs imply a standardized symbolic language that has not been fully decoded, raising the possibility that Sukuh operated not merely as a ritual site, but as a medium for transmitting conceptual frameworks that have since been partially lost. Candi Sukuh exists in a highland tropical environment characterized by heavy rainfall, high humidity, and intense biological activity, conditions that typically accelerate the degradation of exposed stone surfaces, with annual precipitation in the Mount Lawu region exceeding 2,000 millimeters. Yet despite these factors, the core structure has remained intact for over 5 centuries. And while part of this durability can be attributed to the inherent resistance of andesite to chemical weathering compared to softer sedimentary materials, the observed preservation suggests additional factors at play, particularly in the arrangement of terraces, which facilitates efficient water runoff and prevents prolonged pooling that would otherwise accelerate erosion. And subtle gradients across platform surfaces indicate intentional design choices aimed at directing water flow, even in the absence of visible drainage systems. And when compared to other regional sites constructed with similar materials but lacking such optimized layouts, Sukuh demonstrates significantly reduced degradation, implying that its builders possessed a practical understanding of environmental dynamics and designed the structure not for ornamental longevity, but for functional resilience under specific climatic pressures, revealing an engineering logic that integrates material science and landscape adaptation in a way that is rarely emphasized in traditional interpretations of ancient architecture. The placement of Candi Sukuh on the western slope of Mount Lawu introduces another layer of complexity, as the mountain itself holds long-standing spiritual significance in Javanese tradition associated with ascetic practices and sacred geography, and preliminary studies suggest that the main axis of the temple may align with specific solar positions during certain times of the year, although the evidence does not reach the precision observed in sites such as Stonehenge or Angkor Wat, and the surrounding topography creates natural horizon lines that could have been used as reference points for observational alignment, indicating that the site's orientation may not be accidental, but instead integrated into a broader system of landscape-based cosmology. And if such alignments were intentional, they would situate Sukuh within a global pattern of ancient structures designed to interact with celestial cycles. Yet, unlike more mathematically explicit systems, the alignments at Sukuh appear subtle, suggesting either a different degree of precision or a symbolic rather than strictly observational purpose, leaving open the possibility that the builders prioritized experiential or ritual alignment over exact astronomical measurement. So, what do you think? Was this a forgotten engineering method, a symbolic system we no longer understand, or something else entirely? Share your thoughts in the comments below. In the dry northern plains of Sri Lanka, the ruins of ancient city of Polonnaruwa stretch across a landscape that appears at first glance predictable collapsed temples, weathered stone, and silent reservoirs. Yet beneath that stillness lies a contradiction. A city that functioned as a fully integrated hydraulic and architectural system nearly 1,000 years ago, with a level of precision that modern engineers still struggle to fully explain. The most unsettling detail is not its scale, but its consistency, because water still flows where it was meant to, structures still stand where stress should have broken them, and carved granite surfaces reflect a level of finish that, by modern comparison, resembles controlled machining more than hand carving. Polonnaruwa does not just suggest advanced knowledge, it suggests a system of applied engineering that appears complete, yet left no clear record of how it worked. Unlike sites dramatically uncovered in a single moment, Polonnaruwa emerged gradually through colonial-era surveys in the 19th century, particularly under British archaeologists mapping ancient Sri Lankan capitals, and excavations throughout the 20th century revealed not just isolated monuments but an interconnected urban system composed of reservoirs, canals, religious complexes, and administrative zones. Each excavation phase added a new layer, uncovering hydraulic infrastructure beneath visible structures and alignment patterns beneath apparent randomness, ultimately transforming the site from what appeared to be scattered ruins into a coherent model of engineered planning. At the heart of Polonnaruwa lies Parakrama Samudra, constructed under Parakrama Bahu I in the 12th century. Often described as a sea, yet in reality, it is not a single reservoir, but a network of interconnected tanks, covering roughly 2,500 hectares. Scientific analysis of the system reveals several anomalies, because channel gradients are controlled within extremely narrow tolerances that prevent both stagnation and erosion. Stone sluices regulate pressure with a precision comparable to later hydraulic systems, and sediment control mechanisms indicate long-term environmental planning rather than short-term utility. Modern hydrological studies suggest that maintaining such flow stability requires careful calculation of slope, volume, and seasonal variation, yet no measuring instruments, surveying tools, or mathematical records have been found to support how these calculations were made. For comparison, Roman aqueducts such as those supplying ancient Rome achieved gradients as precise as 1 in 3,000, while Polonnaruwa's canals, in some sections, demonstrate comparable or even tighter control, despite operating in a monsoon-driven tropical environment where water levels fluctuate unpredictably, which implies either that measurement systems existed but left no trace, or that knowledge was transmitted through methods we no longer recognize. Carved directly into a single granite outcrop, the Galvahara complex includes 4 statues, the largest reclining figure extending over 14 meters in length, and granite, with a Mohs hardness between 6 and 7, is notoriously difficult to shape, meaning that even with modern steel tools, achieving high surface smoothness requires extended abrasion and polishing processes. Yet at Galvihara, several features immediately stand out, because surface finishes approach a uniform smoothness with minimal visible tool marks. Curvature transitions in facial features and drapery appear continuous and controlled rather than segmented, and symmetry across large surfaces is maintained within visually negligible deviation, suggesting a level of precision that appears disproportionate to the tools traditionally attributed to the period. When compared to other rock-cut sites such as Ellora Caves or Ajanta Caves, a clear difference emerges, because those sites preserve abundant chisel marks that reveal step-by-step carving processes, whereas at Galvihara those intermediate stages are largely absent from the final surface. Experimental archaeology suggests that ancient craftsmen may have used abrasive slurries composed of quartz, sand, and water to grind surfaces over extended periods, but attempts to reproduce the exact finish observed at Galvihara have proven inconsistent, and even under controlled conditions, achieving such uniformity across large granite surfaces remains time-intensive and technically demanding. One hypothesis proposes a multi-stage process involving rough chiseling, followed by systematic abrasion using progressively finer materials, while another suggests that the scale of labor, possibly involving hundreds of artisans working in coordinated phases, may have enabled an unprecedented level of control. Yet both explanations leave a critical gap, because neither fully accounts for how precision was maintained across the entire surface without reliable measurement systems. This leads to a central, unresolved question that continues to challenge both archaeologists and engineers. How was such precision achieved, verified, and preserved across scale in a material as unforgiving as granite? Using tools that should have limited that level of refinement, structures such as Rankoth Vihara demonstrate another anomaly in the form of long-term stability without the use of modern cementitious materials, as bricks appear to have been fired at unusually high temperatures, increasing both density and compressive strength. While tight jointing minimizes voids and distributes structural load evenly, and there is also evidence suggesting the possible use of organic or mineral-based bonding agents that may have degraded over time. Material analysis indicates that some bricks approach compressive strengths comparable to lower-grade modern concrete, but more importantly, the structural integrity of these buildings appears to rely not just on material strength but on geometric distribution, with load paths carefully managed through shape and placement rather than chemical bonding. Unlike Roman concrete, which relies on chemical cohesion, Polonnaruwa's architecture appears to function through mechanical equilibrium, where each element supports and stabilizes the others in a self-balancing system that has remained intact for centuries despite environmental stress. The broader layout of Polonnaruwa suggests deliberate planning, as religious, administrative, and residential zones are clearly separated. Major structures align along consistent axes, and water systems are integrated directly into the urban framework rather than added later, indicating a level of coordination that implies centralized planning or at least a highly structured tradition of design. Comparisons with Mohenjo-Daro reveal similar zoning logic, while Angkor demonstrates comparable hydraulic integration. Yet Polonnaruwa distinguishes itself by compressing these features into a more tightly coordinated system, where water management, architecture, and spatial organization operate as a unified whole. The absence of master plans or written blueprints complicates interpretation, raising the possibility that the city either emerged from a single guiding vision that was never documented, or evolved through iterative expansion guided by inherited knowledge systems that were transmitted orally or through practice, rather than text. But regardless of the process, the final result behaves less like a collection of independent constructions and more like a fully integrated engineered network. What do you think ancient engineers truly knew, and how did they achieve this level of precision? Let me know your thoughts in the comments below. Perched above the Danube River in southern Germany, Heuneburg Hill Fort does not behave like a typical Iron Age settlement north of the Alps. It looks imported. Around the 6th century BCE, in a region long assumed to be dominated by loosely organized tribal groups, a fortified urban center emerged with planned streets, social hierarchy, long-distance trade, and most unsettling of all, a defensive wall built not from timber or stone, but from Mediterranean-style mud brick. That single anomaly reframes everything, because mud brick should not survive here, not in this climate, not in this cultural context, and yet the archaeological record shows that it did, forcing a complete re-evaluation of what we think we know about early European societies. Archaeological work at Heuneburg began in the 19th century, but systematic excavations intensified in the 20th century under German research institutions, gradually revealing that this was not a simple hilltop fort, but something far more complex. Early digs, exposed fortifications, and domestic structures, but the turning point came between the 1950s and 1970s, when archaeologists uncovered the now famous mud brick wall, an architectural feature previously unknown in Iron Age Central Europe. As excavations continued into the early 21st century, aided by modern geophysical surveys, the scale of the site expanded dramatically. transforming the interpretation of Heuneburg into a settlement covering nearly 100 hectares, with population estimates between 3,000 and 5,000 inhabitants, a figure unusually high for the region and period. Burial mounds scattered across the surrounding landscape, many containing rich grave goods, indicate the presence of a powerful elite tied to long-distance trade networks. While each excavation phase added new layers of complexity, including imported Greek ceramics and amphorae, clear evidence of craft specialization, such as metallurgy and textile production, structured urban layouts divided into functional zones, and monumental fortifications that stand apart from anything else known north of the Alps, reinforcing the conclusion that Heuneburg was not peripheral but central, not primitive but organized, and not isolated but connected. The most controversial and technically puzzling feature of Heuneburg is its fortification system, constructed around 600 BCE, consisting of a stone foundation topped with sun-dried mud bricks and finished with a layer of white lime plaster, a method strongly associated with the Mediterranean region rather than Central Europe, where fortifications of the same era typically relied on timber-laced earthworks or dry stone construction. From the perspective of material science, the choice of mud brick appears fundamentally flawed for the upper Danube climate, where annual precipitation often exceeds 800 to 1,000 millimeters, and seasonal freeze-thaw cycles accelerate material degradation, especially in unfired clay structures composed of clay, silt, sand, and organic temper such as straw, which inherently possess limited compressive strength and poor resistance to water erosion. In Mediterranean environments, where rainfall averages between 500 and 700 millimeters annually, mud brick can endure for long periods with maintenance, but under Central European conditions, its survival should be significantly reduced. And yet, archaeological evidence indicates that the Heuneburg wall remained functional long enough to serve as an effective defensive structure. One possible explanation lies in the application of lime plaster, which acts as a semi-permeable barrier, reducing direct water penetration while allowing internal moisture to evaporate, thereby slowing structural decay. But what makes Heuneburg exceptional is not merely the use of this technique, but its consistent and deliberate implementation, suggesting a level of engineering awareness rather than trial and error experimentation. Comparisons with Mediterranean sites, including Greek colonial settlements such as Massalia, reveal conceptual similarities in construction, yet the distance between these regions spans hundreds of kilometers, crossing multiple cultural boundaries, making simple imitation unlikely. Instead, the adaptation observed at Heuneburg implies that the builders not only acquired foreign knowledge, but understood it well enough to modify it for a harsher environment, transforming a fragile material into a viable defensive system. This raises a deeper and still unresolved question: whether this knowledge arrived through direct contact, the movement of skilled craftsmen, or a more complex network of technological exchange that has left no written trace, leaving behind only the physical evidence of a system that should not work but did. The outer surface of the fortification was coated in white lime plaster, creating a visually striking structure that would have stood out dramatically against the surrounding landscape, potentially visible from great distances along the Danube corridor. And while its practical function likely involved protecting the mud brick core from environmental damage, its uniform appearance suggests that it also carried symbolic meaning. In many early urban societies, monumental architecture serves not only defensive purposes but also communicates power, organization, and permanence. And comparative analysis with Mediterranean settlements shows that whitewashed walls were often associated with elite or sacred spaces, implying that Heuneburg's fortifications may have functioned as both a physical barrier and a visual declaration of authority. This dual role transforms the wall from a simple engineering solution into a statement and intentional projection of identity, suggesting that the builders were not only solving environmental challenges, but also shaping perception, turning the settlement into a focal point of political and cultural influence. Material evidence confirms that Heuneburg was integrated into extensive long-distance exchange systems, as demonstrated by the discovery of imported goods from ancient Greece, including fine ceramics and amphorae used for transporting wine and oil, which appear in quantities suggesting sustained and repeated contact rather than isolated encounters. The Danube River likely functioned as a major trade artery, linking Central Europe with Mediterranean markets. But while the movement of goods is well documented, the transfer of knowledge remains more difficult to prove directly. Nevertheless, the architectural evidence at Heuneburg strongly implies that technological ideas traveled alongside physical objects. The presence of Mediterranean-style construction techniques in combination with imported artifacts suggests that interaction went beyond trade, potentially involving itinerant craftsmen, diplomatic exchanges among elites, or the deliberate adoption of foreign innovations. Although no written sources survive to explain the mechanism, leaving archaeologists to reconstruct these connections solely through material remains and comparative analysis. The scale and organization of Heuneburg challenge long-standing assumptions about the nature of Iron Age societies north of the Alps, as the settlement exhibits characteristics typically associated with early urbanism, including a large population, spatial planning, economic specialization, and hierarchical social structure, all of which distinguish it from smaller and less organized contemporary sites in the region. With an estimated population of several thousand inhabitants and a surrounding landscape structured by elite burial mounds and satellite settlements, Heuneburg appears to function as a central hub within a broader socio-economic system, prompting some scholars to propose that it may correspond to Pyrene, a city mentioned by the Greek historian Herodotus, although this identification remains speculative. Regardless of its exact historical identity, the site clearly demonstrates that the level of complexity achieved by Celtic societies during this period has been underestimated, requiring a reassessment of their technological capabilities and cultural interactions. Heuneburg ultimately forces a reconsideration of technological boundaries in the ancient world by presenting a case in which a community located far from traditional centers of innovation not only adopted foreign construction techniques, but successfully adapted them to local environmental conditions, raising a series of unresolved questions that continue to challenge modern scholarship. Why was mud brick chosen despite its apparent disadvantages in a high-moisture climate? What specific modifications allowed it to endure? Who possessed the expertise required to implement and maintain such a system? And why does this level of architectural sophistication appear so rarely in the surrounding region? These questions point toward a broader issue, suggesting that technological exchange in the ancient world may have been more complex and more widespread than previously assumed, involving networks of knowledge transmission that are only partially visible through the archaeological record. So, what do you think? Was this knowledge imported, or something far more advanced lost to history? Let me know your thoughts in the comments below.